Okay. Okay. Hello, sir. Can you hear me? Ravi
Yeah,
sir?
yeah, yeah. Yeah, it's fine.
Okay.
It's
Okay.
fine.
Then it is fine.
Thank you,
Okay. So,
Samrish.
okay. Then.
मैं दे दूंगा अभी थोड़ा रुको थोड़ा रुको मैं दे दूंगा अरे साथ में कौन से ये क्या वहाँ पे क्लिक करना है आप मुझे जो ये तो लिंक नहीं है क्या आपके पास आपके पास वो लिंक
Hello, good morning. So here Professor Supreme Ranjan Das is here. Hello. So I cannot see.
Yeah, we don't see his name in the participants list.
Yes, I cannot also see. I just let me call the Ankur. Maybe he has his number. So good morning, all of you. So just wait for a few minutes. So because other people are coming, joining, and those participants who are joined in the direct link, so they are requested to switch off they are mute themselves, and other people, those who are joining the conference website, there you don't have to do anything. So because there are two types of viewing, the one is the direct link, another is the indirect through the website. So we have, in this session, we have three distinguished talk, and we are waiting Professor Supreme Ranjan Das. Professor Supreme Ranjan Das, are you here? I cannot see here, but the other speaker are there already, Professor Amrish Ghosh and Professor Prasanna Kumar Sahu, and also our session chair, Professor Pankaj Srivastava sir, also there. So maybe 1 or 2 minutes we'll wait, then we'll start. And Dr. Binayak Kamble is here. Dr. Binayak?
I don't see him also, is it?
No, I cannot also see him. Otherwise, we can, if Professor Supreme Ranjan Das is not here, we can start with the oral presentation, because we cannot change the invited talk for like Professor Amrish Ghosh and these things, because maybe other people will join at that time if they are interested in that particular talk. Conference website, like Sumit, are you here?
Yes, sir.
So do you have the phone number for Dr. Binayak Kamble?
No, answer that list we don't have contact number, but we have only mail ID.
Okay. So I'll just wait for a few minutes. Professor Prasanna Sahu, are you here also?
I'm here, yeah.
Is it okay for you to start your talk first and then we'll go? Is it okay if Professor Supreme Ranjan Das is not here?
Yes, we can start.
Okay, then. Okay, so good morning, all of you. So I request all the people, please switch off your mute yourself, then feedback will not come. So whenever you are talking, that time you can switch off. Professor Prasanna, you can mute yourself now. So other people. So good morning, all of you. So those who are direct link or indirect link. So I welcome all of you for this 2D materials and devices. Like third day session 1, and this session we have 3 invited talk and 1 oral presentation. And for this session, I am requesting Professor Pankaj Srivastava from IIT Delhi to as a session chair. So Professor Pankaj Srivastava is a full professor at Physics Department, IIT Delhi. He is also head of the Center Research Facility, where IIT Delhi is spending a lot of money for setting up the advanced research facility. Also, he is the principal investigator for the Sathi project, which is also the setting up the advanced research facility at IIT Delhi. And he mainly works on the different semiconductor materials for their fundamental study as well as device applications. He is a well-known person in the PECVD of silicon nitride and carbon nanotubes. So I'm not wasting too much time. So I'm requesting Professor Pankaj Srivastava to chair this session. Sir.
Thank you, Samresh. So if I've understood correctly, Professor Sahu will give the first talk, the first invited lecture. Am I right?
Yes, sir. Yes.
Okay. So good morning, everyone. So we have, as Samresh said, 3 invited lectures and 1 oral presentation in this session. So we will be starting, there's a slight change in the program. We will be starting with a talk from Professor P.K. Sahu. So he is a professor at IIT Kharagpur at present, and he's an experimental condensed matter physicist and has a broad experience in the study of different low-dimensional materials. He obtained his PhD in physics from Homi Bhabha National Institute and has also spent several years in the State University of Campinas, Brazil, and University of South Florida, USA, and also spent some time in University of Cambridge. Uh, Dr. Sahu's work covered various areas of nanomaterials, that including 2D materials and heterostructures, group 3-5 based semiconductor nanowires and sensors. And his current research focuses on the exploration and understanding of exotic 2D materials. Okay, so the title of his talk is Plasmonic Sensitization of Graphene Devices. So I request Professor Sahu to deliver his talk.
Okay.
Thank you. A request to everyone, please mute everyone. Yeah.
Okay. Thank you, Samaras. I would like to thank you, Samaras, for inviting for this very great conference, and also for the organizer. So my title is not exactly that. Okay. So my title is about emerging 2D lateral heterostructure for optoelectronic applications. So I will, in this talk, I will discuss about how we can make like this new class of 2D material, how can arrange them at atomic precisions, how to make unique heterostructure, and which have very external properties in connection with optoelectronic devices. Already, Professor, like so many great talks are there. Where can you hear me properly? Is it clear? Is my
Yes.
voice clear?
Yes, go ahead.
Okay. So there are already a couple of good talks where you can see that the conventional transistors are deviating from the Moore's predictions. So because of we are reaching the increasing thickness limit, where this new class of a 2D material can cope up or can be integrated with the conventional system in order to achieve the objective of the world demand in terms of electronic devices, where the electronic devices in neuromorphic computing, in-memory logic, those kind of things will take a bigger shape by 2030. And we can see why 2D material can cope up, because if you see the conventional semiconductor like gallium arsenide, silicons, and those kind of materials, at the moment you reduce the thickness, their mobility drastically go down. Whereas if you take the 2D materials like MOS2, MOSE2, then WSE2, WS2, so in this class of material, the mobility reasonable, very good in terms of at that ultimate thickness limit. That's why it can be a potential candidate to replace the or to integrate with the conventional system to achieve the objective. In addition, we all now very very reluctant or very we like our electronic devices to be flexible. It should be like our mobile devices to be like flexible, smart watches, smart biomonitors, wearables, smart glasses, smart tablets. So there are many ways people want like more flexible and transparent electronic device. At the same time, it should have high performance and ultra thin body. So on the other hand, one can see, we can in this present world, you can find Wi-Fi signal everywhere in the any corner of the world you go. So whether can we harvest this Wi-Fi energy into our to recharge or to sell power our electronic devices. In this front, there are already some effort have been made by some MIT group where they use this kind of 2D material, MOS2, 2H and 1T metallic and semi-metallic like PN junction to convert this Wi-Fi band into DC current. That is a starting point where like big things can be done and to make it a scalable process so that we can harvest our energy that has been generated worldwide. So I don't want to give an introduction here in this topic because already people have know that. So what is interesting here because this is the unit cell of hexagon, the trigonal prismatic structure of a bulk MOX2. MX2 M meant for the molybdenum or tungsten, where X meant for sulfur, selenium or telluride. So the moment you go down with a single layer, this is the breaking up symmetry that give rise to many external properties to this 2D material. So you can see in the 2D material, when I say monolayer, that means it is a metal layer in the middle and a two chalcogenides layer on the top, and which thickness, thickness of 0.6 nanometer. And if you take a bilayer means the distance between its total height will be around 1.2. But when I say bilayer means it's total 6 atom thick. But in for the 2D community, when we say bilayer means two layers of layered material. What most striking point is in this kind of class of material, the bulk is indirect band gap. The moment you go to the single layer, so it is converted to the one direct band gap semiconductor. That means your photoluminescence efficiency can increase significantly as the moment you thin down the material. Here we can see that in case of a single layer, you see a strong photoluminescence emission from this kind of materials, whereas in bilayer and trilayer, the photoluminescence efficiency decreases. Without further delay, like unlike graphene and boron nitride, in PMD, there is another striking properties that the valence band are degenerated that give rise to the observation of or valleytronics, the valley Hall effect. So that means you, in addition to electron spin and the charge, you have a valid degrees of freedom. That way you can manipulate the material in a multi-fold way. So another more important frontier in exciton physics, that's what I don't see many people in better talk, they didn't cover it, about the exciton in 2D material, very important, because the moment you thin down to a single layer, because of the reduced screening, we can see that binding energy of exciton in 2D material increases. Sometimes we can get binding energy of a WS2 is nearly half electron volt, so which is tremendous. That means most of the photoluminescence, if you one will measure, that will be dominated by this emission of exciton. So excitons are very important from point of view of quantum computing. So in addition, also you can find a single layer can absorb almost 10 to 20% light for monolayer. So which is significant. Unlike graphene, we cannot absorb that much. So that means this kind of ultra thin material can be useful for also photoluminescence and solar cell application. So there also it is very nice to see that many exciton complexes it can form. It can attach to another electron. It can form charge exciton, or we can sometimes say trions. So sometimes we can form also bi-exciton. We publish some with the magnetic field that we can apply it so that exciton can combine form bi-exciton. Bi-excitons are behave like a boson. So condensation, those kind of things one can observe. And very recently with the Venkatesan group yesterday, he gave a very nice day for yesterday, gave a nice talk. So where we also in collaboration they develop a discover the polaronic trion for the first time. Where what is the objective is the trions carry some angular momentum that can only coupled with the rotational orbital of the substrate or the rotational orbital of the underlying substrate. So give rise to that trion can coupled with this rotational phonon mode that can give rise to polaronic trion, which is very interesting. The binding energy you can see can increase up to 60 to 90 electron milli electron volt. So that the excitons, this nice idea is once the exciton forms, it can behave like a free particle that can move on the surfaces, right? So based on that idea, the from Switzerland, the group, Switzerland group, they demonstrated that you can use the exciton as a switch instead of like photonic device. You can send in information in this atomically stacking different heterostructure. You can form a interlayer exciton. That exciton can diffuse at the surface, and with a gate control, you can make exciton based switches. And also you can remember, in case if you want to make a photonic device, at that in your light wavelength should be comparable with the thickness, so that but we don't need that concept. Now we can convert that information to a exciton. That exciton can carry information. So now there are many more new concepts are coming. Like if you have a single layer, if you stack another layer, you can see there is another virtual pattern it is forming. That pattern eventually called Moore pattern, that can act like a localized trap of exciton and can be localized like quantum emitter. So those kind of concepts are coming on there. This field is now like booming. Like many new phases are emerging in this field. If we can see that you have a extreme flexibility to adjust the rotational angles and to tune the material or phase property. So we have a lot of many flexible way to harness many exotic physics inside this kind of materials. And before going to heterostructure, I will just give a brief idea. Heterostructure are meant for like you have a material A and another material of a different band alignment. If you stack like AB configuration, it will form heterostructures. And if your barrier thickness is thin enough, then the adjacent electron wave function can superimpose that can form mini bands. That means these bands are very good for like you can imagine you have a lot of different states to access, so it will be good for neuromorphic computing, or also even good for some multi-junction solar cell where your efficiency you can improve even beyond the theoretical efficiency, right? So in this kind of 3D materials, what do people can do this kind of heterostructure in vertical configuration? It is easy, but nobody ever have shown that you can make connect atoms in the lateral geometry. So this is where my contribution to make this field is first we develop a method where indirectly or in situ in a one-pot method, we can connect atomically atom by atom and stitch atom in a lateral direction, which is not otherwise possible in any other conventional technique that I'm going to talk. So there are different type of heterostructures. There are type 1, type 2, type 3. Depending upon the band alignment, something will be good for laser, something will be good for solar cells or exciton-based devices, and this band-to-band tunneling type like PA tunneling devices. And one can see from here very nice table from this calculation. There are many different kind of 2D materials here you can find, and you have a lot of many possible way to combine different 2D material to form different type of heterostructure. That means you have enormous possibility. And in 2D material one, from physics point of view, you can remember in the 3D bulk semiconductor, all your diffusion across PN junctions happens due to the diffusion and depletion region. But here, since these are already in atomic resolution, on the limit of atomic resolution or limit of atomic thickness, your carrier transfer will take place via tunneling. That's why carrier can move ultra fast manner, or we can have ultra fast charge transfer process. And also we need very less energy. Means with less energy you can turn on these kind of devices. And however, the field is from point of light emission or solar cell application, the field is limited because of there are very many extrinsic factors that limits its theoretical efficiency. Because growth is again making high quality materials is a big challenges till that, and also there are many extrinsic parameters further understanding is required in order to overcome this to improve the efficiency of this material. That means there are ample room for further improvement for future or future further research. With this, My plan of my talk is I will talk about how we can make this kind of unique heterostructure, which is really technical challenging, but rather how we can solve it from commercial point of view with rather a very simple and cost-effective technique. So in this kind of heterostructure, we can show how we can integrate it for different applications, how we can modulate their phases, and how we can modulate their charge, valley, and spin in order to observe exotic properties of this material. From the first point of view, how to make a scalable means material growth. That's what our groundbreaking contribution to this field, where we have in the CVD method is a simple method using water vapor and hydrogen as a reducing gas. We can switch material from one to other, like with transistor we can switch material from one and exactly and at atomic resolution, means a single atom level, we can control lateral directions, so we can make lateral superlattice. So also I'll show you some of the light matter interaction studies, how when a laser light interacted with the material, how we can again we can convert locally one metal to other, and also we can see other recently how we can manipulate their charge. We can long-term charging and discharging in this kind of lateral electrostructure. I will show at the end. It's a recent study, very recent this year. So in the excitant front of view, I will touch upon few things. So depend upon the time, and mostly I will focus on also device using this kind of a lateral electrostructure. From nanoelectronics point of view, we can show how the transport properties, PN junction diode characteristics, and photovoltaic and light emission characteristics. So, and at the end, what I can tell you is that there are many new physics are still emerging in this class of material when you stack them or you modulate their phase by many extrinsic factors, so that even if you cannot observe magnetism topology in their Ball counterpart, one can readily observe magnetism or topology, even if unconventional superconductor one can observe. That means this field is still booming for new discoveries. Many more new things are also expected. With that, as I told, the making of heterostructure in a direct process using transition metal chalcogenides was a challenging task from last 6-7 years. So you can see that there are many multiple processes like single step, two-step, and patterning multi-step growth, whereas those are recently. They are all are in nature science or in this kind of big paper, because this was a grand challenge, and you will not find many paper in these years because it was the growth mechanism was unclear, and there was no clear cut way or reproducible was a big issue. From this point of view, we come up with that our finding that with a simple using water vapor and as a oxidizing gas and hydrogen as a reducing gas, we can make very exotic and we can make unique structure that was never before imagined even. So we can see that we can molybdenum tungsten, and we can control absolutely the thickness, size, layer number, many things, and also doping or alloying, even many things we can do with this flexible system. So it is still till now it is the most flexible and scalable process for realizing this kind of heterostructure. And future aim is to make 2D and 3D superlatives to combine and to make very unique like logic and memory, this kind of devices. So that's the grand aim vision of this kind of materials. So before going to the more main part of device, I will give some brief idea about how to grow this kind of systems, because CBD is more promising because this is we in this method will allow us to grow in a large scale materials. So we also low cost effective and it's stoichiometry we can easily control. So here is a simple method. What we discovered that you add some percent of water vapor in your carrier gas, and this act as your oxidizing gas, and this act is your hydrogen act as a reducing gas. And when you allow one gas at a time, so what will it will only one material will evaporate in that point, and you can grow the particular one material at a point. So how the selective growth of molybdenum and tungsten domains occurs is, so you can see here when you grow when you send this kind of carrier gas, So only molybdenum domains grow. When you grow, suddenly switch to argon and hydrogen gas. When you then you start growing the tungsten domain on the edges of your molybdenum domain. And if you switch between these two carrier gas, like you turn off and on, then you can go again. You can go the MOX domain, and this is how you can see that a single crystals where you can see more than 50 to 100, around 100 micron size. You can make this kind of single crystal. They are well shaped. That means they're grown very well. So I'll just give an idea about because the growth mechanism there's a lot of story behind it, to validate the growth mechanism because the mechanism was puzzling because water will oxidize both molybdenum and tungsten compound. But why it will growing only one metal? That was a big puzzle to understand. So, to validate that, I did almost more than hundreds of experiments in that time when I was a postdoc that time. So to validate that mechanism, then to take all the precursors like oxide precursors, all these to see what are the real compound are coming out. It was found that molybdenum tungsten they behave very uniquely with water vapor. In molybdenum, when you interact with the water vapor, it forms a small amount of molybdenum dioxide. So that will be more volatile, and when you that is become more volatile and it leach from the surface and go and deposit on your substrate at a relatively low temperature. Whereas tungsten, whatever, this is more oxidizing with the time. This is more stable in water vapor condition at that high temperature, and it forming more higher and higher stable oxide phases like tungsten tungsten WO2 through WO3. So there are in between there are several intermediate stages like W 18 to 48 like that. So you can see how complicated the mechanism were involved. So this is how this table and these don't contribute to the growth, and that's why during the water oxidation condition we only grow the molybdenum. The moment you suddenly switch to tungsten, it can start this one or reduces with the hydrogen, and it can grow only the tungsten. Oh, this is why it is very unique. And the moment you change the stage one between one and two, you start creating this structure, lateral heterostructure. So it is we can see not only one layer we can grow in the lateral direction, we can also grow in simultaneously in the bilayer form. That was our recent paper. You can remember the CBIT process are really very complicated because there are a lot of thermodynamic process, flux, kinetics, van der Waals interaction, edge energy, a lot of processes are involved. So because rather we come up with a very simple method how to control the layer number. The moment you want single layer or bilayer, we can tune that. So by just changing the kinetic coefficient, you can see you can increase the temperature just about 20 to 30 degree. We can make a control to bilayer. So this is how we can go. I am not going to deeper. What I can show you, this layer metal is again very easy to characterize because their absorption coefficient for monolayer bilayer is significantly different. We can, and with the monolayer is almost 10%, that we can easily see it in our standard optical microscope. If a monolayer bilayer, we can distinguish, and if you have a PL, that also way we can distinguish is monolayer and bilayer. And the Raman spectroscopy, which is a fingerprint of any materials properties. If you to take a Raman spectra in each point, you map the whole surface, take images, and you scan the intensity in this particular band of the Raman chip, centimeter inverse. Then you realize only at 240 centimeter, only this material present. That means this belongs to molybdenum. At a 250, and only tungsten is present. That way we know that your material is spatially distinct. And if you take a position map, you see what are the main intensity varies within this position. You can see also how many ways so that the domains are spatially isolated. And you can see with that we can get multi-junction, we can make many more junction, and also sometimes we can get single crystals of nearly 300 micron. That is tremendous. We can make bigger crystals, single crystal, all are well shaped and with laterally connected like that. You can think about making circuit out of it directly. So we also further characterize this kind of material with similar process like Raman. You choose the band, you see the how narrow bands are also present. You choose the peel and you merge, you can see very unique way how the domain are very conformal way or coherently they grown on the edges of one another materials. So selectively. So this and also for many electronic application point of view, one have to understand the interface characteristics. Suppose when you are making a PN junction, one should know how good the interface is. That also depend. That also depend on that also affect the material properties. So in this junction, one can get the information of the junction with this high resolution transmission electron microscope image, where you can see the tungsten domain are almost very high quality, and also there is mild doping of tungsten, but we can see at the end we have the sharp transition of a tungsten to molybdenum domain, and here or we can have a diffuse transition. That means we have absolute control of making this transition. Depending on the type of application, one can tune exactly the shape of the interface regions, and we can from the line map we can already one can identify the PL mapping on the line map whether you have a sharp junction or a diffuse junction that correlate accordingly. So I'm not going to talk too much on that. Similar manner, we can grow not only selenide based, we can go molybdenum sulfide based. So we can see this is also different shape because of different atom molybdenum sulfur to selenium or this kind of ratios. From chalcogenides to metal ratio that accordingly their shape can vary. Also, we can see how nice interface one can observe with the selenide sulfur. Not only that, this material effectively we can form alloys. So we can see this internal energy of a mixing, and the formation of the mixing is minimum for a wide range of selenide to sulfide. That means you can tune exactly their properties, molybdenum selenide to sulfide. Molybdenum will keep fixed. You can tune the between the sulfur to selenium content, and you can tune the band gap. Exactly, we did that same way. With that, you can see that by applying we can observe the individual alloy composition in this maintaining the lateral heterostructure geometry. With the high resolution TM, we can also see their coordination. And the composition one can exactly calculate, or the approximately one can calculate using the Vegar's law, where you can one can apply. So what our unpublished work here, what we saw that we can systematically tune the interface characteristics from tungsten selenide sulfide to molybdenum. That means we can expand the spectrum of available 2D metal for a wide range of application for LED, for example, and for solar cell. We can observe or emit different band of energy. So the different shape are just to give an idea. We can see in selenium it is triangular, going towards sulfur is more like this kind of truncated shape. In between, depend on the composition, whether it is a selenium rich or sulfur deficient, your shape varies. So I am not talking more because of the interest of time. So we can see we can make also lateral super lattice with the fine grains. We can see is a nano PL image where because this cannot be resolved with conventional Raman spectrum. So we can go with the FMT to the laser and we get a tip enhanced PL. We can see locally what kind of PL quenching are appearing at the interfaces if there is a native defect. So again, it's a similar manner, we can make this heterostructure of a vertical heterostructure. Vertical means we can still make a lateral heterostructure in our in a controlled manner. We make a bilayer of individual domain. You can make for selenide, sulfide. You can make superlattice. Bilayer, why are interesting that bilayer can host lot of different kind of excitons. So in direct exciton A, B, and also indirect exciton that you can see in molybdenum sulfide, mostly PL structure dominated by B exciton and A exciton. Then you have lot of different. So there is another method which, as I mentioned, we have a like nanoscale laser light. You can tune. So this is not allowing me to. There is a video. What we can show here, we can convert molybdenum sulfide to selenide using laser light. You can locally dope it and you can convert one metal to other metal. I'm not going to talk in details. I'm going to the device part. Well, you can see the 2D material are already some papers are developed that 2D material because we can easily, unlike conventional 3D materials, to mobilize your this mobile charge centroid, we need to apply more gate bias, whereas 2D material, already the charge carrier confined, little gate bias, one can easily modulate the field or modulate the charge carrier. So already there are a lot of concepts are already made using to make vertical heterostructure using 2D materials or lateral like a heterostructure tunneling field effect transistors. So there's a lot of different concepts were already made. But what is interesting that already in the previous talk they mentioned this is a more important parameter for the transistor to act as a switch, larger on to off ratio. This is where we observe that in our lateral heterostructure, one important point one can see, we have lateral heterostructure MOSE2, WSE2. You make different kind of electrode we fabricated. Suppose you want to characterize the MOSE2, you make the electrical connection between 1 and 5, what we can say all are ohmic contact. If you measure the electrical transport between 5 and 4, what we can see with under positive gate bias only in give a current IV characteristic like that. If you have negative gate bias, only you can get a conductivity of the I then current in this domain, negative side. That means if this is behave like a rectification process is going on. It's like a typical characteristics of a diode. So that means you can see how oversimplified we have the process that we can fabricate directly PN junction without making any doping, exchange doping anything. And these our devices are already made based on Ashgren sample. Most of the device you can see in terms of mini 2D paper that exfoliated to a boron nitride substrate. But here we fabricated everything on a on as grown substrate. That's why still we can get a photo like on-off ratio of the order of a 10 to the power 5, 10 to the power 6. Since you have a PN junction, if you shine light of a different power, you can see the current is increasing. That you can see that it can be act like a photosensor. And but in bilayer, however, we got more interesting properties because accordingly, for material thickness is more, we have a more number of carriers. That's why you can get suppose you shine light. What we observe similar like diode like response. In addition, we got a short circuit current that is at zero gate bias voltage. That means because of the inbuilt potential of different light, when you apply different light, because of the inbuilt potential across the PN junction, so give rise to short circuit current. That is a typical signature of photovoltaic effect. That means this material can be act like a photovoltaic devices at this atomical thin limit. These are the detailed transistor characteristics. So we can show that we can evaluate the short circuit current, open circuit voltage, electronic power maximum, and fill factor. What I would like to point here. So because many conventional process people calculate the area based on that because vertical heterostructure is easy. But if you calculate based on the lateral junctions, if you take area of the junction or width of depletion regions, so we got efficiency of more than 100%. That means it's not the like it's not usual. So what instead we fabricate different width to see that how the area is scaling. We did that power conversion efficiency. So later on we evaluated that our power conversion efficiency is the low, which is typical in that reported values in case of TMDs because the metal is really thin. But if you take usual theoretical depletion lead width, we can get efficiency up to 1% or 2%. So open question is in like many people, they talk about the area calculated like that, whether in lateral function, how to exactly calculate the area. That means you have to rescale or rethink the equation. We have to modify for this kind of atomical thin sample. Yes. For electroluminescence point of view, there are many device concepts are made, like to make PN junction, or there are many impact excitations. Like interlayer exciton is more like only suppose you make a heterostructure, one metal, then lateral, you connect another metal. and your band gaps are aligned like that, so that your carrier can electron can go downhill, hole can go uphill, and they can recombine, can emit light. And this is why interlayer exciton are very important for quantum computing or quantum emission purpose. So there are some people's effort in monochalcogenide, like in single metal, they electrically tune the gate, apply separately, and this is how their efficiency is very low, but it was a clear demonstration of the performance as I see. But in case recently they develop or like the monochalcogenide, they can observe bright, dark exciton, and bi-exciton based emission from this kind of TMB. Overall, the quantum efficiency is low. However, we can make heterostructure. What we demonstrate that in case of bilayer, we significantly saw a significant light emission from this material at this energy. The main challenge is we supposed to see the energy corresponding to the interlayer exciton. However, we see a strong emission in WS2 because the region is not known, because maybe there is some charge transfer mechanism is predominant that give rise to this kind of things. That in order to understand that, we did.
Professor Sahu, kindly wind up your presentation.
Yes, another one, two slides. So in order to understand that, with a scanning near microwave impedance spectroscopy, so what you can see, how is a scanning spectrum, you can get a conductance and capacitance. You can see long-term charging. If you vary the energy, you see the molybdenum domains are charging with the time and with the energy, and slowly tungsten. That means long-term charging. Charging or residual free carriers can seen up to 72 hours. So same thing, we can also see laser on and off. We can see the charge carrier retain there up to 20 minutes, 28 minutes from when you laser off. That means with photocurrent conductivity mapping, when you shine light, you first create the carriers generated at the molybdenum domains. Eventually, they move across the domain. That's why you can observe long-term charging and discharging occurs in this material. So there is a unique way, many things to probe the interface characteristics. With that, I am doing. The future is demand that we can integrate different kind of device in communication, computing, sensing in one device. That means the field of 2D heterostructure is really emerging. In this 2D pattern, we can attach many kind of component. We can make realize many devices. With that I end up with that, we can see that we can make atomic low power optoelectronics with this latent heterostructure. I acknowledge my previous groups at South Florida and the University of Cambridge, and with my recent collaborator. And we are just starting our life with PhD student and postdoc, three students. Thank you very much for the attention. I will happy to take some questions.
Thank you, Professor Sahu, for a very exhaustive and interesting talk. We can have a couple of quick questions.
Yes, sir. I have a question. So, what is the heterojunction width in the MOS2WSCT heterostructure, and how the excitons behave there, like in the form of if you see recombination time or length?
Okay, heterojunction is depend. That's what I told. We can tune it. Suppose if you want make we can achieve up to 1 nanometer width, up to hundreds of nanometer width, like variation in the composition. Okay, that in that, let us go to the here. Suppose you can see in this bilayer, so the TM, oh sorry, okay, here you can see here. So we can make at most 1 nanometer. Means atomic scale, even if the resolution up to 1 nanometer, we can make heterojunction, like one precisely atomic thickness. Or in my previous slide, where I can show that we can tune their properties. Okay, somehow it is okay. Sorry, it is somehow. Okay, so exciton, once it is formed, it can move across the surface. Here, so one can tune the junction width. So depending upon suppose how there is extensive work we do, means in terms of when you are moving from tungsten to molybdenum, means you are changing from one gas to other gas. So you cannot, if that time you can adjust, and that accordingly you can make a systematic alloying at the junction. So moving from one metal to other material. Or one can, if you want absolute clear domains, you have to switch one material and wait for a couple of seconds, 10 seconds, then you start the other gas. By the time it grow and stop, the other material can grow at the edges. This is how we can adjust that.
Okay, thank you.
Okay.
Any other question? Otherwise, we will go to the other next talk. Okay. So I'm informed that unfortunately, Professor S.R. Das won't be able to deliver his talk because of an emergency at his end. So now we are going to the next invited lecture. This will be delivered by Professor Amish Ghosh from ISC Bangalore. Professor Ghosh graduated with 5-year integrated MSc in Physics degree from the Indian Institute of Technology, Kharagpur. And he completed his PhD in Physics from Brown University, where he worked on electron bubbles and superfluid helium. From 2005 to 2009, he was a postdoctoral fellow at Harvard University, working on optical and hydrodynamic properties of chiral media. And in the year 2009, he joined Indian Institute of Science, Bangalore. His research interests include the study of quantum fluids, plasmonics-driven colloidal systems, and their applications in biotechnology. So the title of his talk is Plasmonic Sensitization of Graphene Devices. So I invite Professor Amrish Ghosh to deliver his talk. Thank you.
So some noise is coming. Who is PD? Please mute yourself. PD is mute yourself. Okay. Okay, now it is fine.
Hello, can you hear me? This is Ambarish.
Yes, it is clear.
Okay, great. Yeah. Thank you. Thank you so much for the kind introduction. And I hope you can see my PowerPoint screen, PowerPoint slide.
Yes, it is
Great,
fine.
great. I would like to thank the organizers for inviting me to give this seminar. Thanks, Ankur, for reaching out and inviting me. It's a great pleasure, and it's wonderful to listen to these exciting talks. I request the coordinator to please let me know maybe about 25th minute or so of my talk, because I believe my slot is for half an hour.
I will do that.
Try to wrap it up. Great.
Yeah.
Great. Thank you. So my name is Ambarish, and I'm at the Center for Nanoscience and Engineering at ISC Bangalore. And I'm going to talk about some integration of plasmonics with graphene devices for different types of optoelectronic applications. The way I have planned my talk, I'm going to give a somewhat quick introduction on 3D plasmonics, try to go a little bit into the the motivation of what we are trying to do and what our experimental platform is, and give you a particular example of graphene plasmonic photodetector, and then point out the many unresolved issues and hopefully some of the things that we will be able to show in the future. So that's all I plan to talk about. A brief introduction about plasmonics. So plasmons are quantized, collective, and coherent oscillations of the free electron gas that are typically seen in metals, noble metals like gold, silver, and also aluminium, and in recent times in some of the new alternate materials as well. Now, it's very difficult to excite plasmons using light, bulk plasmons using light. For that, however, plasmons that are localized to a surface of a metal can be excited using light due to certain symmetry considerations. So these surface plasmons, which are confined to a surface or an interface, can be broadly divided into two classes. One is called surface plasmon polaritons, which are propagating plasmons, in which these plasmon waves they occur at the interface of a metal and a dielectric. And there is a very specific phase matching condition that is required to excite them, in which both the direction as well as the energy of the light would have to is important. A somewhat easier plasmonic resonance to excite would be the localized surface plasmon resonance and LSPR. And these are non-propagating, that is, they are localized, and they are typically, they happen by metal nanostructures, and in which the plasmon interaction, the plasmon excitations are confined within the particle volume, within the particle surface. And these can be excited by direct light illumination. Now, LSPR, the localized surface plasmon resonance, is known to depend on size, shape, of the material. Just one equation, effectively, all that you are talking about here is the dielectric constant of the metal nanoparticle, can be written in terms of, with respect to some constant here, epsilon infinity, the plasma frequency, which depends on the properties of the electron gas inside the metal, and the light frequency. And then effectively, the resonance happens when the dipolar polarizability, for example, that of a sphere, it's given with 3 times epsilon times particle volume times this particular formula, where epsilon depends on the dielectric constant of the metal and epsilon m is the dielectric constant of the surrounding medium. Under certain conditions of light frequency omega, the real part of the denominator goes to 0, and that results in a large polarizability, which can be shown in terms of either scattered or absorbed light, and that is effectively your localized surface plasma resonance. Okay, so this is sort of a 1 minute introduction to plasmonics. Let me go a little bit more into what's extremely relevant to this talk, and this is related with interaction of plasmonic particles. So if you have 2 plasmonic particles, in which you can imagine that the polarization of the light is parallel to the interparticle axis. So in the picture that you are seeing at the top, the light, for example, is going into the screen and is linearly polarized, and the linear polarization is along the direction that is shown here. One sees that depending on the gap between the particles, one would have depending on the gap, the optical absorption spectrum would change. And also, what is not shown here is at the junction of the particles, there will be an extremely large electric field enhancement. And you can think about it from the perspective as if like there are electrical dipoles that are aligned end to each other. And as a result, the electric field at the junction becomes very large. So this is an ideal configuration in which you will get an extremely large field enhancement at the junction. Okay, and this is sort of the driving technology for something called surface enhanced Raman spectroscopy, in which molecules that are present at this junction, their Raman scattering signal would go up by orders of magnitude. Something that is not very good for large field enhancement would be, for example, when the light polarization is perpendicular to the interparticle axis, and in that particular case, the electric polarization would be parallel to each other, not collinear like here, and as a result, they would repel each other, and this does not result in a very large field enhancement. And this is also sort of can be seen from some energetic arguments in the optical absorption spectrum. Okay, so this is ideal for large field enhancement. Just for the sake of completeness, I must tell you, these things happen when things are very close together. So in fact, the strength of these field enhancements go as 1 over the separation cube. On the other hand, one can even think about some sort of a diffraction-based sort of a feature in which you can think of arrays of particles, and even they show some sort of resonance. And these resonances happen when the distance between the particles and the phase difference between the optical waves has certain relationship. So this is not too relevant to the talk that I'm giving here. Out here, what I'm going to tell you is almost entirely, is very strongly dependent on this near field enhancement. So localized surface plasmon resonance requires metallic nanostructures, I've already told you. By coupling 2 localized surface plasmon resonances, you can give rise to extremely large electric field. So the question that we asked is, well, all of the previous work was done in 2 dimensions. Can we try to think of a smart way in which we can get this coupling done along the 3rd direction, okay, in the z direction, for which we needed to place metallic nanoparticles in arbitrary geometries in 3D. And how do we do that? For this, we used a technique called glancing angle deposition, in short form GLAD. And the way GLAD works is it's a physical vapor deposition scheme in which you take a material, you heat it up, it evaporates, and then the substrate is kept at a very extreme angle with respect to the direction from where the vapor comes. So the angle alpha here can be as high as 85 degrees or so. It's really a glancing angle, okay? So at this very sharp angles, you have an enhanced effect of shadowing. So basically, once a little bit of material is deposited, subsequently there are regions that get shadowed because of this extreme angle. Okay? And using this, people have shown in the past, you can manipulate the substrate, and using this, you can create all sorts of different interesting structures. I'll not go into the details of this, but just to show you, these are all the structures that are theoretically possible, and all of these things have actually been experimentally achieved in different labs. Okay? So you can have a wide variety of shapes and structures. Now, having said that, glads and metals don't really go with each other very well. And this happens because, when this material comes at this extreme angle where alpha is 85 degrees or so, this whole technique relies on shadowing, okay? But metals, because their melting temperature is somewhat low compared to dielectrics, they tend to diffuse around, okay? So the success of glad really depends on substrate temperature to the melting point ratio. For metals, it's somewhat low. So as a result, if you want to do successful glad deposition with metals, you would also have to reduce the substrate temperature. And in some of the slides that I'm going to show you later, we have reduced our temperature of the substrate to cryogenic temperatures. We use liquid nitrogen, and during evaporation, the substrate temperatures were about 140 to 180 Kelvin. So, okay? So once again, the motivation, the localized surface plasmon coupling is of great interest, and GLAD provides unique geometries and variety of three-dimensional structures, including metals. So how these two come together, and this is a really, really old work, I think almost 8 years old now. What we showed long time back was, well, you can start imagining some sort of a layer-by-layer deposition in which you have this dielectric, metal type of a structure. And this could be done very easily using GLAD. And what you're seeing here, these stripes correspond to silver layers. So, each of these rods correspond to 3 silver islands. And you can increase the number of layers very easily. This is something that's showing 6. And, this sort of gave rise to a very interesting technology platform altogether, because what you're talking about is enhancing the plasmonic coupling along the 3rd dimension. And you can do it also on regular arrays like the way it is shown here. And in this particular case, the regular array was made by nanosphere lithography. On top of it, this sort of 3D structures were formed, and you can get a coupling in the Z direction. So with this as the basic experimental platform, let me try to go into a little bit of how 2D materials comes into the picture. So the plasmonic near field, which happens at the junction of nanoparticles, used for a variety of different applications. One of the earliest is known to be SIRS, in which 2 random silver colloids, if a molecule happens to be at the junction of the 2 particles, even the Raman spectrum of a single molecule could be detected. So there is tremendous enhancement of SIRS. Okay, this is used for photocatalysis, photovoltaic applications, and what's very relevant here, related with also photodetector type applications, in which you have this nice heptamer type of a structure of gold islands on which a layer of graphene was put, and then the near field along of this heptamer geometry resulted in high field enhancement or high photoresponsivity of this graphene device at certain wavelengths. So our experiments are similar to that. Just to tell you a little bit about what happens when you have just a single particle, if you shine light, you will see a large electric field shown in red around here. If you think about 2 particles, and here we are going to tell you about a dimer geometry in which you take 2 metal nanoparticles, you shine the light, and you have a gap of d between them. In this particular geometry, of course, as you can see, the light polarization doesn't really matter. It's always perpendicular to the interparticle axis. If you do this calculation, you will see that, a large field enhancement happens at the junction. Here, the gap D is taken to be 7.6 nanometer. This is just a representative picture. And then if you can vary D, so for example, here, if you're looking at the electric field, the maximum electric field enhancement as a function of wavelength, you will see that as you reduce the gap from 34 nanometer to 2.8 nanometer to 0.34 nanometer, things increase in log scale. And in fact, for D, for sub-nanometer values of D, the electric field can be as high as 10 to the power 6 or so. So this is a tremendously large enhancement. Okay. Now, so as one would imagine, people have tried to fabricate these nanogaps in literature. They have used this random colloidal aggregates, different types of lithographic techniques, so on and so forth. And all of this has resulted in more or less controllable gaps down to a few nanometers or so, maybe 2 nanometers. And then there are questions of uniformity, reproducibility, scalability, and all of this. So how small does one need to go? I've said my simulations go up to 0.34 nanometer, but what's the problem in going another 3 orders of magnitude smaller, at least in simulation? Well, smaller is not necessarily better. And although a classical calculation, what I've shown here, the maximum the electric field as a function of gap keeps on going high as you reduce the dimer gap, this particular calculation does not allow for the electron tunneling from one particle to another. Okay, so remember, when you shine light, the plasmonic particles are, the electrons are oscillating between the individual particles. The classical calculation does not allow the electrons to tunnel from one electron to another. So a more detailed quantum mechanical model that allows for this quantum mechanical tunneling sort of says that, well,
Hello?
Hello?
Oh, sorry.
Yeah. The electric field enhancement will not continue to rise once you reduce the gap beyond a certain value. Okay? So if you remember your quantum mechanical tunneling equations, there is a strong exponential dependence, and as a result, below a certain gap, the electric field does not get enhanced anymore. Okay? So there is an optimal gap at which you will get maximum possible enhancement. And this particular thing has been studied in the past. And it turns out that, well, depending on the material, 0.3 to 0.5 nanometer is almost ideal. And this was done both experimentally as well as there were theoretical calculations that sort of shows that, beyond 0.3 to 3 to 5 angstroms, the electron tunneling will really start taking over. And as a result, there will not be any electrical field enhancement. Okay? So, and this is where the 2D material comes in. Graphene is one of the thinnest materials that can act as a spacer between two plasmonic particles. In addition, it also has a very broadband optical broadband optical transmission and optoelectronic properties going all the way from 200 nanometers to 6 microns. In addition, it can also be functionalized. It can be, you can probe it using Raman spectroscopy, so on and so forth. There has been work in which graphene has been used as a plasmonic, as a spacer between this type of plasmonic geometries. In this particular case, this is a work from the last group, in which what they have done was to take a metallic nanoparticle and put it on a metal film, and in which they were separated by a layer of graphene of 0.34 nanometer. And they showed that indeed there was a large field enhancement at the graphene junction, as and which might be suitable for search type application, but such a continuous metal film will not allow you to harness the photovoltage or in sort of photoresponsive. Okay? So the ideal configuration, according to us, is given by, well, some substrate in which you take plasmonic nanoparticles, you put a layer of graphene in which you have another array of graphene plasmonic nanoparticles. The way we fabricate this, what we defined as the ideal geometry, we started with a monolayer of silica beads. The silica beads effectively gives you some sort of a pattern on which the subsequent fabrications are done. Here, the size of each bead is about 500 nanometers. On this, we come at an angle, a layer of silver. Okay, so the substrate is at 80 Kelvin. Well, that was the target temperature, in which we deposited a layer of silver. So the silver, because of this extreme angle, only ended up at the top of your silica beads. Subsequently, we annealed them, and once you heated them up, each of these silver blobs effectively turned into small particles of the order of 150 nanometers or so diameter. On this, we transferred a layer of graphene. This layer of graphene, sort of because of the distance, sort of nicely, it was not sitting tightly, but sort of it conformed around the plasmonic particles like this. And this conformity is important because what we do, as you can imagine, well, this is the way it looks. You can't see the conforming from this view, but a side view does confirm that it sort of nicely conforms around the plasmonic particles. This conformity is important because we next want to do another layer of glancing angle deposition with exactly the same way. Everything is cooled down to cryogenic temperatures. The second layer of silver comes, and what's important is the second layer of silver deposition and a subsequent annealing results in the so-called ideal geometry, in which the two plasmonic nanoparticles are separated exactly by a layer of graphene. And this is what you are seeing in this SEM image. In this particular case, for example, if you concentrate on where my cursor is, what you're seeing at the top is slightly brighter silver nanoparticle. Then there is a layer of graphene, and then there is a slightly dimmer silver nanoparticle, which is underneath the graphene layer. Okay, so what you have is a geometry like this. All right, and they are all approximately separated by 500 nanometers. In order to see whether indeed we have a very large electric field enhancement there or not, we looked at the Raman spectrum of the graphene layer, and what you are seeing is a humongous increase in the Raman scattering, going from bare graphene to the graphene within the diamond layer. So there is a humongous increase in area and height of the peak, including the defect, and this is sort of an issue that one needs to sort out. The defect peak is also showing there. If you look at the Raman measurement a little bit more carefully, you can take a Raman map, and you will actually see some sort of a pattern that sort of vaguely resembles the array in which the plasmonic near fields are kept. Remember, the gap between the plasmonic particles was of the order of 500 nanometer, while the excitation wavelength was 532. Focused down to about 700, 800 nanometers or so, which is why it's not super sharp. But it does still show a pattern which is sort of the hotspot pattern, which suggests that indeed the maximum Raman signal is coming from the junction. The calculation of the Raman enhancement showed that the overall area under the peak for both 2D and G peaks went up by a factor of 20 and 3 respectively. In order to understand this further, we looked at the electric field enhancement. This is still classical standard electromagnetic calculation as a function of wavelength. And we found out that, and we said that, well, the Raman enhancement should come both due to the enhancement at the excitation wavelength, here, which is 530 nanometer. And depending on whether you're looking at the 2D peak or the G peak, there will also be enhancements coming from these two ranges. So this is the formula that one uses, and based on this, you can also calculate the theoretical enhancement, which actually turns out to be not too far off from what we experimentally measured. So which sort of gives us confidence that indeed our understanding of this system is reasonably right. We subsequently went ahead and tried to measure the photovoltage. The experimental platform is shown here. We have a source at the drain, and then this is the silver dimer with the graphene layer in between. We just did flood illumination. Remember, this is really a wafer scale technique. I mean, although this is 400 microns, there is nothing in this technique that doesn't allow you to go up to a few inch square sort of substrates, or even really large area substrates. It's not a problem. Okay, so we did this photovoltage measurement over this large area, and what we see, depending on the wavelength of light, we do see a large photocurrent. This is some sort of an on and off ratio that you are seeing here in both blue and green, and none in the red. And to understand whether this makes sense or not, well, I don't think I should here. So the photoresponsivity that we have observed, the maximum photoresponsivity that we show here, turned out to be of the order of few ampere per watt, which is approximately 500 times more than, at least 500 times more than the graphene sample that we had, bare graphene without any plasmonic particles. And I must tell you, this is significantly more than the previous volumetric-based photodetectors that were shown in the past. Okay, so this is one of the highest plasmonic-based photovoltage enhancement in any graphene device that was published some time back. There are some subtleties. There are certain subtleties that I would like to point out here. And this is where, again, we go back to the plasmonics origins. In this particular case, what you are seeing is a simulation where you've taken two gold particles. In between, you have, let's say, this is the graphene layer, and you have shining light from the top. This is our experimental geometry. The experimental, the numerical simulations suggest that the extinction shows some pattern like this, in which you have two peaks. And without going too much into the, well, let's look at this particular peak, which corresponds to 665 nanometers, which is shown here. And what I've plotted here is the electric field profile at the junction of the two particles. Okay. So what you are seeing here, and this is kind of interesting actually, at 665 nanometers, if you look at the charge distribution, it goes from negative here to positive in this direction, and negative out here to positive in the other direction. So what you are seeing effectively are two dipoles that are oppositely aligned to each other. Now, if you were to remember what I showed you right at the beginning of the talk, is that when you have light, when you have the light polarization parallel to each other but not collinear, this does not give rise to large field enhancement. But why is it that we have a large field enhancement in this particular case? The answer to this is kind of subtle, in which we have to consider the size of the particle to wavelength of the light that you're using. To understand this particular configuration, what you have here, the light actually goes from left to right, that is along the z direction in this particular picture. The light is polarized in the plane of the screen, that is, along the xy direction. And just concentrate on this part. The wavelength of the light is almost comparable to the particle size, in which what happens, because of retardation effects, the dipole moment, the phase of the light which is pointed, which causes a dipole moment from bottom to up along the positive y direction, along the positive x direction, is different from the direction of the dipole moment induced in this particular particle. Okay, so this particular configuration that I've shown here, in which the direction of the light and the interparticle axis is in the same direction, the electric field will only get enhanced if the size of the particle is comparable to the wavelength of the light. The dipole moment in the particle needs to point in the opposite direction to that of the bottom particle. And this can happen when the radiation, which is comparable to the wavelength, is comparable to the size of the particle. So this is a subtlety which shows that this particular configuration does not work for small particles, but would only work for particles that are, let's say, larger than 200 nanometers. Okay, so if you want to try to adopt this to your geometry, this is a very important thing that you need to note in your overall design strategy. Okay. So in summary, so this particular numerical part was done, was published in this paper in collaboration with Professor Asu and I think a group from materials engineering. So in summary of what I have said so far, I hope I have a few more minutes. There is a very novel technique of getting a very high near field enhancement. It gives rise to one of the highest voltage in hybrid graphene plasmonic devices, and you have atomic control on the separation. And in the paper at the top, Vasu's group had shown that it is possible to also get a similar type of structure using wet chemistry, where it's also some form of a directed self-assembly, but that does not depend on GLAD or any physical vapor deposition. So more on this, in the paper. I have not gone into this. A few unresolved issues that I want to point out. One of them is, if you just take the simple case, the experimental results that I've shown you, the graphene layer was sandwiched between silver nanoparticles. We also investigated the simple device of just graphene on a silver device. Let's not go into the details of the fabrication, but here what you're seeing is a graphene layer that goes on the top of a silver nanoparticle. So okay, a layer of silver particles. One of the simplest things that you can do. When we looked at the photo response of this particular device, again, it's just, we had a variable light source, variable wavelength light source, and we focused it onto the photo detector, and this whole experiment was done in vacuum. We have shown, we have observed some sort of a photocurrent, and we have also observed the photocurrent to be a strong function of wavelength. The real question, and this is where the unresolved part comes in, is in the photoresponsivity. Although not shown here, there is a small plasmonic enhancement that is seen in the photoresponse around 330, 350 nanometers. However, a much larger photoresponse is observed at a smaller wavelength. Okay, this is shown here, in which the photoresponsivity goes as high as 10 ampere per watt in a wavelength range of about 270 to 60 nanometers or so. Okay. I wanted to understand this because it just doesn't make sense why this is as high as 270 nanometers. We did some control experiments in which the same device were done where silver was replaced by gold. And what is amazing is that the gold responsivity does not give such a large responsivity at 270. In fact, we could not see anything below 350, although a little bit of a plasmonic peak could be observed for gold. Same with the silver, we could observe the plasmonic peak, but in addition for silver, we see this large responsivity at 270. So it's apparent that silver does play a crucial role. We tried to understand it from simple classical electromagnetic simulations. Again, there is no reason why there should be a large electric field enhancement at about 270 or so for either gold or silver. So this is one of the unresolved issues. Now, one of the perhaps clues is that for graphene, the Van Hook singularity, in which there is a very large enhancement of density of states, happens at about 250 nanometers or so. So there is something about silver that's resulting in enhanced light matter interactions around the Van Hook singularity, and that's all we know. The control experiments does not show clearly whether there can be either strain or doping that is going to play such a large role. So we do not. So this is one of the unresolved issues that we are yet to figure out. With respect to future plans, and this is an experiment that is being pursued in the group right now, in which graphene has been replaced with some diacyl cogenides, in this particular case WAC2, and this can result in a programmable, not really programmable, an array of single photon emitters. And preliminary studies are showing extremely promising results. Hopefully, we will be able to tell you more about this in the near future. So, I would like to acknowledge my colleagues, Murugesh, Arindam, and Vasu for the collaborations. Most of this work is done by Debodrita, sitting here with contributions at the later stage from Preeti as well. Okay, so with that, I would like to thank you for your attention.
Thank you, Professor Ghosh, for a very informative talk, and you presented it in a very lucid manner. I really liked it. So now the talk is open for questions.
Hi, my name is Krishna. Could I ask a question?
Yeah, please go ahead.
Professor Ghosh, it was a great talk. I have a curious question. So you did this photo response experiments. Was the light polarized? If it is not, I'm just curious, what does your random polarization of the light incident on your nanoparticles, what does it do to your response? Could you elaborate on it?
Good to talk to you, Krishna, after so many years.
Thank you.
So, Krishna, what you have to remember here, you see, let me just try to find this out. You see, this is where the geometry comes in. Sorry. Okay, maybe I'll just show it here, this particular one. Yeah. You see, here you're talking about the light wavelength, light coming from the top to bottom, okay? Right. So you see, the polarization of light is always perpendicular to the direction of light propagation, right? Right. So if you see from the top, it is actually circular symmetric, which is why you do not have any polarization dependence, and this is something we have checked also. As expected, you do not see any polarization dependence in either the photoresponse or I believe we also tried it in Raman. We do not see anything. Okay, it's circular symmetric. You see, you are looking at a sphere at this dimer along the interparticle axis, so it doesn't matter which direction your light polarization is. I hope that answers your question.
Right. Yeah, great. I got it. Thanks.
More questions?
Hi, this is Samaresh. So, in the last where you saw this silver has shown like the very high responsibility in the UV or in the they are below 300 nanometer. So, did you consider like if even thin layer of silver oxide is there any like how these things will change? Because of the gold, there will be no like a oxidation, but if thin layer, very thin layer, like silver oxide is there, then because silver
Indeed.
oxide.
Yeah, but so that's a absolutely valid question. It is very possible that the silver has a very thin layer of oxide, but exactly how does it result in such an enhancement in 270 nanometers? Because we have also done the similar things for other oxides. What is so special about silver oxide? I mean, maybe it is, but it's not clear to us at least, what the exact mechanism is going to be. Do you have an idea on how it might result in such a large photoresponse at 270?
I don't know. That's why I'm thinking actually.
Yeah. No, I mean, please let us know if you have a good idea. We would like to solve this problem.
Okay.
I can tell you, we have done both Raman as well. This is something that Preeti really looked at very carefully. She looked at the doping as well as the strain that are created, and it does not seem to be none of the magnitudes are large enough to explain such a dramatic behavior at 270 nanometers. Okay, something unresolved.
Any other question? So if not, let us thank Professor Ghosh once again. And now we go to the last presentation. Yeah, thank you very much. So now we go to the last presentation of this session. So we have an oral presentation by Dr. Vinayak Kamble. Dr. Kamble right now is an assistant professor in Icee, Thiruvananthapuram, Kerala. And he has completed his PhD from IISc Bangalore. The title of his talk is Protonic Titanate Nanotube Tubes Composite with Reduced Graphene Oxide for Improved Response Time of Diffusion Limited Hydrogen Sensors. So Dr. Vinayak, you have 15 minutes for your presentation.
Hi, Pankaj. Thanks a lot. How do I share my screen here? I'm new to this interface, so I guess...
there is some share. You can see a share icon at the bottom.
Hello, can you see the bottom? There is
yeah.
mute button.
I have to allow the permission. Just a minute. Yeah, Cisco, I have to allow. Okay, later. Sure. So now I think even come back because it's asking.
So have you joined using the link or using the?
Using the link only. I am link only, but I have just a minute. Now, yeah.
Please go ahead.
Yes.
Okay, so good afternoon, everyone, and sorry for the delay. This title of my talk is basically protonic titanate nanotubes and their composite with reduced graphene oxide for improved hydrogen sensors. Now, why this I chose for the 2D materials? First of all, of course, graphene is there. The other 2D component comes from these titanate nanotubes. Now, how would you say a tube is a 2D? Let's look into that. I have roughly 15 minutes. I'll just quickly show you about this is my research group. These are some of the students. These are PhD students, and some of them are master students. So Shubham here, Kusuma and Archa, they have worked for this work. And we work on various other topics as well. Sorry, we work on various other topics as well, including sensor, thermoelectrics, and solar absorber. Okay, coming back to the topic, we have hydrogen. Of course, we all know that it is a very much promising fuel for the future. The entire theory of hydrogen economy basically rests on that hydrogen has a very high energy of combustion and it can actually act as a very good fuel for a lot of hydrogen-based technologies. But we have to come up with such solutions which will make use of this, and also at the same time, because it's so explosive and it's so combustible, it is also required to have some kind of a safety measures to have control over this hydrogen handling. So if you look at the Google Scholar or something like that, you would see there are number of hundreds and hundreds paper every year coming in for hydrogen sensors, and you would see that many of them would characterize their material for certain response and would say that it is good hydrogen. It is good at sensing hydrogen. Several questions come in like, what is the operating temperature of this sensor? Because for safety, you really want it to operate at room temperature. At the same time, it has to have very fast and quick response of ideally few seconds to lesser than few seconds. And the cross selectivity to other gases should be absolutely not. It has to be very selective to hydrogen compared to especially volatile organic compounds and carbon monoxide and things like that. And overall, it has to have a low power consumption. The basic operation at room temperature, first of all, brings in a low power consumption because you don't have a power consuming heater. And the device has to have a simple architecture which can be user friendly. So chemoresistive sensors have been explored quite a lot, and I will just quickly spend a minute on this. Chemoresistive sensors consist of granular metal oxide, particularly particles. And metal oxides, as you would know, they are very sensitive to the atmospheric adsorption related surface states. And these surface states are either charge donors or charge acceptors. Most likely, the oxygen from the air gets surface adsorbed, and you will have a surface state formed which is electron acceptor, like a trap state, and it will form some kind of a band bending at the interface, and the interface would have some kind of a barrier between the two grains. So now, if you happen to have some reducing gas in the atmosphere, that reducing gas might react with oxygen and would donate an electron, which would kind of reduce the barrier and increase the charge carrier concentration, resulting in changes in the resistance of the material. Now, if this process is so efficient, I mean, the barrier is so large, which is also at the same time tunable, you would have created a very large sensitivity. And for that, people actually looked into various microstructural and compositional changes, and they found that the nanostructured materials are doing better at this job. I'm just speaking in. I think things are all right. I mean, it's working fine, right? I'm just need feedback. Yeah,
It's okay.
It is fine.
sure. Okay, so people looked at some kind of chemical sensitization, some kind of making heterostructures and things like that. When they make some kind of chemical sensitization or heterostructure, there are several mechanisms which set into the place. Let's say you are decorating with some catalytic particles. The only job this catalytic particle does it's contributes into some kind of a spillover effect. The spillover effect helps in dissociation of these gas molecules, and essentially you will have more adsorption of these gas molecules. Correspondingly, the change will be higher. And at times, it can actually have some kind of a metal semiconductor interface, and there could be already some kind of a depletion layer which is formed between the metal semiconductor interface, and that will tune the Fermi level of this semiconductor, and essentially the response will have some kind of an enhancement. On the other hand, you might actually dope in with some material, and that might actually give in some extra donors, extra electrons or holes, and which would participate into this, and they kind of improve the acceptor state, or they also improve the kind of active sites where the gas molecule can bind and things, and so on and so forth. So all of this results into a improved enhancement, rather an enhancement in the sensor signal. Now, one of the major demerit of these oxide is that in order to have efficient surface reaction, which is in the chemisorption domain, it happens at elevated temperatures. So one has to actually improve the response at room temperature, because you want to have a room temperature working sensor, and that is why people look into heterostructures, because they are more see that actually this one can see that this oxides which we have made, which we are making, they can actually give different kinds of phases. And like for example, titanium oxide, which we are considering here, all these rutile, anatase, and bruchite also are known. Quite familiar are the rutile and anatase, which are routinely used for various electronic applications, high K dielectrics and things like that. But titanium oxide itself can act as a good sensor, but the problem is that it would not have any selectivity, and it will also not work at room temperature. So the next, the remedy to that, what we could think of is basically this titanate nanotubes. The titanate things, why I'm saying specifically nanotubes, because they form into nanotube forms. We'll go into that formation later. First, let me tell you that this titanate nano things are actually the same octahedras of titanium and oxygen, but which are separated by some intercalated water molecules. So the moisture is actually trapped inside this. So you can say it as H2O and twice TiO2. Some in between two titanium oxide octahedra lies one H2O molecule. So that makes a unit cell of this trititanate. It can also have normally some sodium or potassium here, which will increase the spacing a little bit. But normally people, which are also useful for charge storage or battery materials, because they can actually have mobility of these protonic species, the H plus or things like that. Now, these materials, whatever we are looking at, how does it forms into a titanium trititanate nanotube forms? You can see here, this is a typical TEM image, and the genesis, the formation of these nanotubes is shown in the diagram here. This is a PRL paper. These people probed this formation of these titanate nanotubes through high-end electron microscopy, and what they proposed is that once this trititanate sheets, which are these are initially formed into some kind of layers of trititanate sheets, and once it forms, the hydrogen adsorption on the surface actually overcomes the buckling, the coupling between the two layers, and it results in buckling of one of the layer, and that kind of rolls up, and it goes on rolling and forms some kind of a nano sheet turned into nanotubes. So you will have these hollow nanotubes of trititanate, which is H2TiO3, Ti3O7. And these nanotubes are, you can see they are having very high surface area, and the essential presence of H2O in between the two layers of TiO6 octahedra actually makes it protonically conducting. The hydrogen is very mobile. It can actually conduct under the action of electric field. So they are called protonic titanate nanotubes. And so we have prepared several composites of these things. First of all, these titanate nanotubes were prepared by solution method. Simple hydrolysis of titanium isopropoxide in water results into amorphous TiO2. Once you put this amorphous TiO2 powder into a hydrothermal autoclave with NaOH and keep it at 200 degrees for 24 hours, it would result into these tubes. First, TiO2, which is amorphous powder, results into these sheets. They buckle into, they form some kind of tubes. We collect it and drop cast them onto this electrodes with gold electrodes, and then we will form sensor device. The other approach that we have found, just to improve the response of this thing, we have actually added reduced graphene oxide into it. Two ways. One is in situ method. That means you either put graphene oxide directly into the hydrothermal bomb, And then what happens is, at the same time when these nanotubes form, that graphene oxide is also in situ reduced, and you form reduced graphene oxide with these trititanate nanotubes along. The other way is both are the graphene oxide is reduced separately, the titanium oxide TNT nanotubes are prepared separately. They are mixed in the physical mixture in a mortar and pestle, which is so we named it as physical hybrid. It's a mixture, and that actually was ground together, and it was broadcasted onto electrodes. So what we actually observed is that compared to the in situ method, the ex situ method actually had better mixing. In situ method, because there was a segregation of RGO somewhere and TiO2 the other ways, so it actually led into some compositionally graded things. So you have a RGO containing things towards the periphery, and the center is essentially only TiO2. So when you are putting electrode, it can actually have two current pathways. So we have characterized these materials with various characterization techniques. The Raman shows signature of RGO in better in case of the physical hybrid compared to the composite, because as I said, composite it is suffering from some kind of a segregation and things like that, non-uniformity. On the other hand, the physical hybrid was very much uniform, and we actually looked at the XPS spectrum, and what we found is that there is a heterostructure formation. Because of this heterostructure formation, the core levels are actually kind of shifting from its regular binding energy position, because the photoelectron which is emitted from these core levels suffers excess energy loss, because it is coming out from a region where the electrons are completely depleted or like that. So the more and more shift is actually a sign that there is more heterostructure barriers which are present in a physical hybrid compared to the regular composite. And these are some of the microscopy images. You can see that there is a good uniform mixing of these 2D sheets of RGO with one-dimensional nanotubes, which are also hollow in nature, and they are having some kind of a composite nature in the sample. So later on, we have actually probed the electrical studies on this. We have done electrochemical impedance spectroscopy just to find out what is the kind of contribution from each of this and the interface between the two. What we found is that the TNTs as such have very large bulk resistance. However, upon putting with the graphene oxide, there is the overall impedance comes down by an order of magnitude. You can see here it from 10 to the power 7 to 10 to the power 6 or 5, something like that. So it comes drastically down. And in addition to that, it also shows a large capacitive contribution, because there are lots of interfaces formed between the RGO and this TNT nanotubes. And that helps in some kind of a parallel channel also. So in case of the composite, essentially, we could clearly see that there are two pathways in which the current can take up. Now, if you look at the Arrhenius plot here, the Arrhenius plot of just TNTs, it is, if you look at the high temperature, it is perfectly linear, like the way you would expect for a semiconductor. However, at low temperature, you would see that it deviates from linearity, and it has rather more conductance at low temperature. And this conductance essentially comes from the protonic conductivity at low temperature. At room temperature, there's a lot of moisture, and essentially it also has intercalated hydrogen, water, and protons. So these protons give rise to protonic conductivity. There are several reports in the literature which have proved this. What we actually observe is that when we put in RGO, the RGO contribution actually somewhat suppresses this protonic conductivity. It might actually be present, but there is also parallel pathway from the RGO in that case. So that has been suppressed, but you would see that it follows more or less Arrhenius for a larger temperature range. We looked at the response of these devices for hydrogen. You can clearly see that C, which is actually the physical hybrid, compared to bare RGO, bare TNTs, and the composite which is made in situ, does far better compared to this, because it has many frequent or very uniform heterostructures which are present inside this thing. The response is gigantic. It's around, for given like 1000 ppm of hydrogen, it's around nearly 1000%. that is like 10 times increase in the current you can see from 0.1 to nearly 1 nanoamp. And on one more thing which you could note here, RGO shows something which is like a P-type response. That means the current drops when you expose it to reducing gas. And all the other composite along with TNT have N-type response. That means the composite is again dominated by TNT response. And it is N-type because when it is introduced with a reducing gas, it has more carriers, and the electron concentration goes on increasing, the current increases. This can be explained by this method. You can have a p-type material. If the electrons are depleted from the surface, you will have more holes on the surface, which forms hole accumulation layer. On the other hand, if the electrons are depleted from the surface of an n-type material, you will have a depletion layer, and that will be less conducting, and so it results in opposite type of resistance change. You can look, we looked at the time response analysis of we did this, and you can see essentially the time of the bare TNTs is it's exceptionally large. It's like of the order of thousands of seconds it takes to kind of come down, or at least for low concentration about of a few hundreds of seconds. Whereas the in situ made composite, which was having the parallel pathways, actually had much lower, one order of magnitude lower response. So and the physical hybrid had something in between. Okay, and this was analyzed with this time constant analysis, and we found out what could be the time constant for these given, and it never fitted with single time constant. It required two composites, two contributions. So we say that we predict that possibly these two contributions have surface and the bulk. That means the surface ionic conductivity of these protonic species which are moving, and the bulk electronic conductivity, which is the charges which are moving. And we plotted these time constant for these concentrations, and there are these reports by some of the researchers who have studied the kinetics and the movement. You could see that there is a relation that time constant moves with a concentration with an exponent r minus 1. So you can find out the value of r, and this r, whether it is equal to 1 or greater than 1 or less than 1, you can actually call it as either linear diffusion, slow diffusion, or faster diffusion. So like for example, r less than 1 is like this. It is faster diffusion. That means the time constant falls off very rapidly with the increasing concentration. And if r is greater than 1, the time constant falls off rather slowly, or it increases with the concentration increasing. And if it is flat, r equal to 1, it has really linear dependence, as you can see. So all this was analyzed, and what we saw is that the physical hybrid actually had a dramatic change from the crossover low concentration region and high concentration region. High concentration region, it had some kind of a fast bulk diffusion, and low concentration region, it had some kind of a linear diffusion. Whereas it was always a slow kind of dynamics for your TNTs.
Vinayak, please wind up your talk.
Sure.
Yeah.
So I would just finally summarize with this mechanism here. When we are making some kind of heterostructure between TNTs and RGO, there is a type 2 heterostructure formed between this a small band gap RGO and TiO2 nanotubes, which are this heterostructure barrier, whether it is uniformly distributed or not, it governs whether there is a parallel contribution or not. And essentially, the heterostructure is the one which is very sensitive to the response, hydrogen. So we are getting better response because of very uniform heterostructure. And this was seen by taking XPS at different regions in the sample. And what we saw is that for the physical hybrid, the spectrum were more or less uniform all over as compared to the in situ made method. And that's why we propose that physical hybrids show much better response times and much better response compared to this ones. And it is much better strategy than actually making in situ composites. And finally, I would like to thank these people, my lab members, collaborators, my institute, the funding agencies, and of course the conference organizers who have given this opportunity for presentation. Thank you.
Thank you, Dr. Vinayak, for a very nice talk. So now the presentation is open for questions.
Yes, I have one question. So
Sure.
for this Langmuir isotherm equation fitting, and you have shown for different R value. So have you
Yes.
taken into account the dissociation coefficient at the interface?
Yeah, all that energy basically that gets the dissociation coefficient gets counted into the adsorption energy. So one can actually say that it is interrelated, but not very explicitly considered.
Okay. Thank you.
Any other question from the participants?
Okay.
So Vinayak, I have one small question
Sure.
regarding your XPS data.
Yes.
So as you can see, you see huge changes in oxygen 1s and carbon 1s. So
Yes.
before taking the data, did you sputter the surface or it was taken on the
Uh,
gas deposited surfaces?
So usually they sputter clean it for the surface, but the thing is that the material was drop casted and it itself was very less thickness. It was taken as it is, but you can see that each of these changes was identified. Like for example, the green one actually was attributed to the lattice oxygen, whereas the blue one, which you would normally attribute for the oxygen vacancies in TiO2, and if you have some kind of heterostructure, that would also contribute into the picture. So, and that was also contributed because of the heterostructure formation. So this shift is uniformly observed all across all the core levels. But in case of oxygen 1s particularly, you get an extra peak because there is something which is possible at the interface between TNTs and RGO, and that might contribute into a different binding energy.
Right. Now, what I was also thinking is that perhaps recording the valence band data would also have been very useful for you.
I have tried. I try to look at usually whenever I get the data, but
Yeah,
one has to maybe we should do the UPS for very good resolution.
that's right, because you are
Yeah,
commenting on transport properties
that's true.
eventually. So it would be very helpful if you look at the
Yeah,
valence
next
band
stage
data
maybe we
carefully.
can. Yes,
Yeah.
sure.
Okay. Thank you.
Thanks.
Thank you. Any
Yeah.
other question from the participants? Okay, if not, we thank once again Vinayak for a very nice talk. And I also thank all the people
Thank
who
you.
have joined this session. I thank all the participants. And now I hand over the mic to Samresh.
I
Thank you.
will. How do I stop this? Stop sharing.
So thank you all. So we are very thankful to Professor Pankaj Srivastava to chairing this session and also all the speaker and all the participants. Our next session will start at 2 o'clock in the same hall 3, for the last session of the 2D materials and devices. We welcome all of you in the next session at 2 o'clock. Thank you. Thank you all.
Thank you.
Hello, this is Ankur here. Am I audible? Yeah.
Yes.
Yes. So I think we can start another 5 minutes or so, 5 to 7 minutes. Now it is another 7, 8 minutes to two o'clock. So this is 1:50, 52 in my watch. So maybe another 5, 7 minutes we can start.
Yeah.
So Dr. Sumanlata Jain, you are there, right? Yeah, I am.
I am here already.
Yeah. Okay. So hello and welcome. This is Ankur Goswami. I think I am audible to all of you. So welcome to the Icee 2020 conference, the last session of 2D materials and devices. So far, we have a very exciting talks were going on, and so it is a very nice experience to listen to all of you. So this is the last session. We have total 3 lectures. So 2 invited lecture and another is oral presentation. So the invited lectures will be delivered by Professor Sumanlata Jain. She is from CSIR Indian Institute of Petroleum, Dehradun, and Professor Krishna Balasubramanian from IIT Kanpur Electrical Engineering, and Mr. Sumit Sharma. So this session will be chaired by Dr. Shamaris Das. Shamaris Das is an associate professor at Center for Applied Research in Electronics at IIT Delhi. He received his PhD in 2011 from IIT Kharagpur, and he worked on germanium quantum dot based floating gates, light emitters, photodetectors, and so on. After that, he has been in Tyndall Institute, and then after he was in Cambridge lab in Cavendish lab in University of Cambridge quantum information and project he dealt with. He has received many awards: Faculty Research Award, Institute for Smart Structure and System, Young Scientist Award, Indian National Academy of Engineering Young Engineer Award, and so on. So now I will request Dr. Das to coordinate this session, to chair this session and continue the session. So over to you, Dr. Das.
Thank you, Ankur. So we have welcome all of you for these sessions. So I am requesting all of you, though, please mute yourself, and those who are direct link joining, and those who are watching, they can watch through the Icee website also. So in this session, we have, as Professor Ankur mentioned, we have 2 invited talks and 1 contributory presentation. So first talk will be given by Dr. Sumanlata Jain. So she is the principal scientist and heading the synthetic chemistry and petrochemia and material science and chemical science divisions at CSR Indian Institute of Petroleum, Dehradun. So she received many awards. I am citing few of them. She is the recipient of and she is a recipient of CRSI Bronze Medal Award 2017, and she awarded INSA Professor for DS Kothari Chair Award, and she also the honorary member of the Indian National Young Academy of Science, and she awarded the Sharp Women Excellence Award in 2013, and she also awarded the INSA Young Scientist Award and also NASI Platinum Jubilee Young Scientist Award. I'm not going all the awards, so and she works on the, apart from the title of the talks, she works on other areas also, like the carbon dioxide for fuels and value-added chemical, photocatalytic activation of organic compounds, and molecular complex and homogeneous catalyst, also specialty additive for lubricating oils. So now I'm requesting Dr. Professor Sumanlata Jain to talk about the 2D materials and their nanocomposite as photocatalyst for conversion of CO2 to chemical. Professor. Hello. Now I'm giving it to Professor Sumanlata Jain. Hello.
Yeah.
So
Thank you,
share
Dr.
your...
for your kind introduction. Yeah, actually there is some problem in the connectivity. So am I audible?
It is fine, perfectly fine. Can you able to share the screen?
Yeah, just now. I'm just sharing my presentation.
Okay.
इस कहाँ पर है? ये है ना? कैसे शेयर होगा? One sec. I'm just sharing.
Okay, no problem. No issue.
नहीं, ये तो खुला हुआ है ना, you are sharing इसका. करो. देखना जरा स्लाइड शो कहाँ पे है. I'm sharing the screen. So is it fine now?
Yes, slide is visible. Now it is fine.
Okay. Thank you. So first of all, I would like to thanks all the organizers for giving me this opportunity. So the title of my presentation is 2D materials and their nanocomposites as photocatalysts for the conversion of CO2 to chemicals. So we are basically working on the CO2 utilization. As we know that due to the current developments and fossil fuel consumption, the carbon dioxide concentration is increasing day by day in the atmosphere. So the increasing concentration of CO2 is a problem. So actually, if we see this graph, that concentration of CO2 is continuously increasing, and the adverse effects of these concentration is the ocean acidification as well as the global warming. So these are the two issues which are affecting over the climate as well as environment and the human beings and all the other living whoever on the earth. So for managing this problem, to manage the carbon dioxide, there are some approaches. First, if we can reduce the carbon dioxide production, but I think it is not in our hands because we have moved towards the development. So going back, it is not possible. So reduction in the carbon dioxide production is little bit difficult. The second one is the carbon dioxide capture. Yes, we can capture the carbon dioxide and we can store it, but it is again a problem because if we are storing the carbon dioxide and if some accident happens and all the carbon dioxide come out, then it will be worst and the problem will be much, much higher beyond our imagination. Last one is the carbon dioxide utilization. I think we have several opportunities in this utilization. Carbon dioxide we can use as a feedstock. So rather than considering it a waste, we can use as a valuable feedstock for the production of chemicals. So our research is basically focused on the carbon dioxide utilization. So if we see some future perspectives in CO2 utilization, if we see at the current today's think we are most of the chemicals which we are getting through the thermal routes. So the carbon dioxide is the consumption of carbon dioxide is very less. In the short term, if we see the thermal routes as well as the algae and in addition to the chemicals, we can also produce the fuel from the carbon dioxide. Similarly, if we look at the long-term approaches, it is thermal, electrochemical, photoelectrochemical, as well as plus algae. So we can use a lot of carbon dioxide, not only for the chemicals, but also for the fuels. And it will really maintain the carbon cycle if we can convert the carbon dioxide into the fuel. Because the most of the carbon dioxide is coming from our transport sector. And if we can use the waste or emitted carbon dioxide again to the fuel conversion, that will maintain the carbon cycle. So this is the most viable approach that we can focus to manage this CO2 problem in the future or in the current recent years. So if we look at the conversion of carbon dioxide to chemicals, actually as we know that CO2 is a C1 feedstock and it can be converted into the any of the chemical that we can imagine. It can be converted into the any organic chemical. For example, methanol, formic acid, carboxylic acid, or whatever we can imagine, we can produce from the carbon dioxide. But problem is not so simple because the main issue with the carbon dioxide is its stability. CO2 is a very, very stable molecule. Due to this, its thermodynamic as well as kinetic stability, you have to put a lot of energy to convert CO2 into any of the chemical. So this is the biggest problem which we have to handle for before the conversion of the carbon dioxide to any of the chemical. So challenges are there. Important barriers, or we can say what are the main challenges behind the CO2 utilization. First is the CO2 capturing, because we know that in the transportation or power sector, the carbon dioxide is generated as a mixture. It is not a pure CO2. So the cost which is involved in the capturing of CO2, its separation, purification, and its transportation is very, very high. The second one, we have to deal with the stability of the carbon dioxide molecule, because CO2 is a very, very stable molecule. So we have to put a lot of energy. So we have to think from where we can get this energy. Similarly, the energy requirement of the CO2 chemical conversion, lack of industrial commitments, because as we know that most of the chemicals are being produced from the Fischer-Tropsch process using the syngas, carbon monoxide. So shifting from the carbon monoxide to carbon dioxide as a feedstock, it's a big challenge, because no industry wants to change the well-established plant or well-established process. So there are a lot of industrial commitments or industrial challenges to shift from the one feedstock to the another feedstock. Similarly, the lack of socio-economical driving forces, because the utilization of CO2 is not economical due to its stability and other issues. So it has a lot of challenges. But if our main research is focused on the photocatalytic reduction of CO2, there are some differences in the thermal process as well as the photochemical process. As we know, in the thermal processes, a lot of energy is required to break the CO2 CO bond to get the carbon from out of the CO2, or for the conversion of CO2, a lot of energy is required. But in the photochemical processes are different. So in the photochemical processes are mainly driven by the radical processes. So single electron transfer is bit easy rather than breaking the bond through the thermal processes. So we are mainly catalytic reduction or photochemical activation of the carbon dioxide for its conversion to the value-added chemicals. If we see a simple calculation, like 10% of the solar energy, out of this 10%, only 0.3% if we can use for the conversion of chemicals, then we can meet the total energy demand of our users. So this is the simple diagram by which we can explain the photocatalytic reduction of CO2. So as the light, this is a semiconductor material. So in the presence of light, the charge separation takes place and electrons move from the valence band to the conduction band, and the electrons which are in the conduction band, they are used for the reduction of carbon dioxide. However, the holes which are being produced in the valence band, they are used for the oxidation reaction. So by this phenomena, redox cycle is complete and the carbon dioxide can be converted into the desired product. But it is not so simple as it is looking. Why it is so difficult? Because the carbon dioxide is a very stable molecule, and the reduction by one electron, it gives the CO2 radical anion that has the band structure. So it is not stable. A lot of potential is required. So if we can look these equations, the carbon dioxide can be reduced to any of the product. It is depending on the requirement of number of electrons as well as the protons. So if CO2 is reduced by the 2 electrons, it can produce the carbon monoxide. That is also a very valuable feedstock for generation of the, or for the production of all the chemicals which are being produced through the Fischer-Tropsch process. Similarly, by the 2 electron reduction, carbon dioxide can be converted into the formic acid. By the 4 electron process or 4 electron reduction, it can be converted into the formaldehyde. Similarly, 6 electrons and 6 protons can produce methanol from the carbon dioxide. And this is the ultimate reduction of CO2 to the methane, which requires 8 electron and the 8 protons. So if we look at the basic requirements, what are the basically required for the CO2 reduction process? So here we can say 2 things are required. One is the 2 things are required. One is the photosensitizer and the catalyst. So if we look at the simple phenomena, this is the Z scheme, that light falls on the one material, it provides the electrons, and these electrons can go into the hole of the in the valence band of the another material that act as a catalyst, and here again the charge transfer takes place, and the electrons which are in the conduction band are required for the or used for the CO2 reduction. However, these holes used for the oxidation. In most of the cases, oxidation of water occurs. So by this process, the redox cycle is complete. So in most of the literature, if we see that semiconductor materials has been used as a heterogeneous photocatalyst, like titania, zinc oxide, and all these materials. But these semiconductor materials have two drawbacks. One drawback is they have the higher band gap. Due to this high band gap, the visible light activity is very limited. We know that in the solar light, only 5% is the UV light, and 45 more than 45% is the visible light. So we target a material that can be activated under the visible light, so that we can use the solar light efficiently. So, and another drawback is the recombination. As I said, that under the light irradiation, charge transfer or charge separation takes place. Charge electrons and holes separated, they again recombined. So deactivation occurs simultaneously. So these two are the biggest problem. One is the higher band gap of the heterogeneous semiconducting materials, and another is the higher recombination rates. On the other hand, these are some semiconducting materials, and their band gaps. So we can see that most of the semiconducting materials are activated in the UV light, and due to the higher recombination rates, they are not very much useful in the under the visible light. So another thing for which we are concentrated, or our main research is focused, are the metal complexes. So we are mainly working on the metal complexes. These metal complexes have several advantages, because they can, due to this extended conjugation, they can be activated in the solar, in the visible light, and due to the metal and CO2 binding, they enhance the concentration of carbon dioxide for its activation, because the central metal can bind with the CO2, so it enhances the concentration of CO2 that is required for the conversion of CO2 to the chemicals. And another thing is that that metal complex is directly involved in the activation of carbon dioxide. So these macrocyclic complexes, which are like halocyanins, bipyridyl complexes, these are they have wide spectrum of absorption, mainly due to this conjugation. They can be they can easily absorb under the visible light. And another interesting thing is that if we change the ligand, by changing the ligand or metal, we can design, or we can tailor our complex like that, so that we can get the desired product. But still, they have some limitations, like metal complexes are less robust, because under the photo irradiation conditions, the ligands are also organic compounds, so they can be degraded. Photo complex can be degraded, and can get means the stability is very poor. Another thing, because these metal complexes are homogeneous, so their recovery is a challenge. We cannot recover, and so the product isolation as well as the purity of the product is bit confusing or challenging. Similarly, the one of the called the sacrificial electron donors, because as I said, when the charge separation takes place, in the metal complexes, HOMO and LUMO separates. So the electrons which are being used for the carbon dioxide reduction, but the electrons can be, to complete the cycle or for the regeneration of metal complex, we have to provide the electrons. So for these electrons, we need to give some sacrificial electron donors. So these, the use of these sacrificial electron donors make the process very much environmentally undesirable as well as the economically. So these are some drawbacks. How can we overcome this? These drawbacks? So we have targeted to immobilize the homogeneous photocomplexes to the photosensitizers, to the semiconducting supports. So what that supports can do, by immobilizing the metal complexes on the semiconductor supports, we can make the catalyst recoverable, and we can enhance the visible light activity. Also, we can stabilize the complex, because our complexes act as a catalyst, and the semiconducting support provide a support for the large charge, for the mobility of the charge as well as the for charge separation. And we can also, in some cases, the semiconducting material itself act as a sacrificial electron donor. So we do not need to provide other reagents like tertiary amines for the reaction. So how this system actually work? After the absorbing light, the homogeneous metal complex transfer electrons. HOMO-LUMO separation takes place, and the electrons from the HOMO goes to the conduction band of the semiconducting material, and the holes which are generated in the valence band. So these electrons which are in the conduction band, they use for the reduction of carbon dioxide. However, the holes which generate in the valence band, they are used for the oxidation reaction. So the metal complex provides the continuous electrons, because in the immobilized system, the electrons are being provided by this molecular complex. So the continuous pumping of the electrons, or the metal complex acts like an antenna. It provides the electrons continuously. So the conversion rates are higher, or the efficiency of the system is much higher rather than the semiconducting materials as well as the metal complexes. So these are some benefits, or these are some advantages of how these systems work and how they get how these are beneficial. So one of the most important support which we have used in our lot of papers, a lot of current research, is the graphene oxide. As we know that graphene oxide is a very fantastic material which is being produced by the strong oxidizing agent from the graphite using the strong oxidizing agent. It has these functional groups, oxygen containing functionalities. So these functional groups can provide the covalent attachment with the metal complexes. So the system is covalently bound, so there is no chances of the leaching. Similarly, these oxygen containing functional group, they provide the dispersion. They provide the dispersion of graphene or the photocatalyst in organic solvents very nicely. So it increases the conversion or efficiency. Graphene oxide itself acts as a semiconductor material. The band gap is 2.43. But to make it visible light active, we can immobilize our complexes on the graphene oxide, and under that our molecular complex acts as a photosensitizer, and graphene oxide provides the charge mobility and charge separation and stabilize the system. So now I will discuss our current research, that where we have used that graphene oxide as a semiconducting materials. So for example, in this case, this is the cobalt phthalocyanine. We have used that functionalized cobalt phthalocyanine immobilized on the graphene oxide. So first, we treated the graphene oxide to enhance the oxygen functionalities by using this sodium acetate, chloroacetic acid, to increase the carboxylic groups. And these carboxylic groups act as a linker, and they combined with the functional groups of the cobalt phthalocyanine, and we get this immobilized system. So this immobilized system is completely leach free, and here cobalt phthalocyanine act as a photosensitizer, and this graphene oxide support it provide the charge mobility as well as the separation as well as the photostability for the whole system. So if we look at our results, the red one is indicate the immobilized system, and this blue one is indicating the 1:1 physical mixture of the carbon, that graphene oxide and cobalt phthalocyanine, and this is the black one is the graphene oxide. So we can see the clear-cut differentiation. The yield of the desired product in case of the immobilized system is much higher. In fact, it is much higher than the physically mixed system. So we can say that covalent immobilization of the complex also enhance not only the stability of our catalyst, but the efficiency of the system. It increases the electron mobility or charge mobility and increases the reduction rate of the CO2. So we can see the clear-cut differentiation that immobilized systems work much better and much higher activity they provide rather than the bare molecular complexes as the semiconducting supports. So next, so change नहीं हो रही है slide.
So if it is audible. If it is not changing, you can stop sharing, again share. It will be right if it is changing.
I don't know why it is not changing. Stop sharing.
Stop sharing also.
वो नीचे शेयर वाला पे क्लिक करेंगे तो उधर आ जाएगा.
Stop sharing.
Stop sharing.
Is it fine now?
Can you? It is visible. Can you change it?
But it is not changed. I don't know why.
So can you stop sharing and then change it? without sharing, and then you share.
Is it the computer is hanged or is it someone?
Okay, you change your slide when computer open, and then you start sharing.
One second. अब शेयर करते हैं एक सेकंड यहाँ से। So is it fine now?
Yes, it is fine.
So if we look at the mechanism of the system, so under the visible light irradiation, as I told, that the metal complex act as a photosensitizer. So homo-LUMO separation takes place, and the electrons from the metal complex goes into the conduction band, and these electrons are used for the reduction of carbon dioxide, and necessary protons we get from the water, because the reaction mixture, the solvent system is the water plus DMF. We are using DMF because it acts as a CO2 philic solvent, so it can capture the CO2. So the concentration of the CO2 in the reaction medium is higher. And here we are using the triethylamine as the sacrificial electron that provide the necessary electrons for the reaction, or to maintain the electron availability for the reduction of CO2. Similarly, in another work, we use the ruthenium trinuclear complex. Here we can see that we have prepared the trinuclear complex. So this is the first step. We prepared the ruthenium bipyridine complex, and this is again we attached with the bipyrimidine, and then we synthesize this trinuclear complex, and that trinuclear complex we attached with the graphene oxide by the similar phenomena. First, graphene oxide was oxidized to this to get the more COH group on the surface for the covalent attachment, and then we attached with the one linking agent, or for ligand that can link our molecular complex, and this is about the final system. These are the characterization of the complex that we prepared to confirm that the targeted molecule or target complex has been synthesized successfully. And these are the characterization of our final molecule. We got the XPS. In XPS, all the desired elements are there. We can see that our complex has been synthesized successfully. Similarly, in the IR spectra, we confirmed. In that time, we can see that this is the graphene oxide layered structure, and these are the complex units. So all these characterization indicated that the desired compound or desired photocatalyst was successfully synthesized. And after that, this is the, in case of the UV, if we see, like this is our, if we see that this is our immobilized system. So in the immobilized system, higher absorbance in the visible light indicated that immobilized systems work better rather than the molecular complex as well as the graphene oxide. So similarly, if we look at the activity, so this is the graphene oxide and this is the geo-attached ruthenium complex. So the activity of, we can see that the methanol yield in case of the immobilized system is much higher, even more than double or more than triple, means much higher rather than the graphene oxide. So these results indicated that the immobilized systems work better, they are stable, and they can provide higher conversion of the CO2 to the desired molecule. We know that if we compare the results with the literature, that graphene oxide has been used as a photocatalyst for the CO2 reduction, but yield of the methanol was found to be very other than in our system. So one more advantage is that here in this system we have not used the tertiary amine as the sacrificial electron donor. We think that graphene oxide itself has provided the electron, or the multi-nuclear units, they have provided the desired electrons for the reduction process. Similarly, in this case, we synthesized the ruthenium heterolaptic complexes. This is the ruthenium bipyridine complex, this is the heterolaptic ligand, and this is the heterolaptic complex. Again, we synthesized and we immobilized the complex on the graphene oxide support, and the system has been used for the conversion of CO2. If we look at all these graphs, this is our final catalyst, and we got the higher, much higher methanol yield as compared to the all the components as well as their physical mixtures. So these results means confirmed our belief or and made us realize that immobilization really can work better. We can plan or we can design or we can synthesize some of the molecular complexes and then find out some semiconducting supports for the immobilization. And those immobilized system can be finally used for the improved CO2 conversion to the desired reactions. So these are similarly, this is the mechanism. This is our metal complex. This is the graphene oxide. Similarly, under the visible light irradiation, the electrons from the molecular complex goes to the conduction band of the graphene oxide, and these electrons are used for the conversion of CO. These electrons, due to this unsaturated support, they get the higher mobility, and finally, so the increased mobility of the electrons on the surface also inhibit the recombination rates. So these electrons are freely used or freely available for the reduction of CO2 to the desired compound. So this is mechanism. The electrons or protons which we want for the reduction process are deriving from the water splitting that occurs at the valence band of the semiconducting support. So in recently developed a similar kind of several systems and successfully used for the reduction of carbon dioxide to the methanol. So finally, I would like to conclude my talk. We know that CO2 is a very, very stable molecule and its activation requires the extensive energy. In thermal processes, the reactions are required higher temperature, but there are some drawbacks. If we give the higher temperature, the coke formation or deactivation of the catalyst is one of the major issues, as well as and the poor conversion of the CO2 to the desired compound is another issue. To overcome these problems, we can think on the alternative or renewable energy, and we are mainly focused on the solar energy because the photocatalytic reactions are driven or governed by the radical formation. So single electron transfer is better rather than that breaking of the highly stable CO2 molecule. So photoredox catalyst occurs because in the electronically excited state can be more easily reduced and oxidized than the ground state. In view of the current scenario, we know that semiconducting materials has been widely used for the conversion of CO2 or in the generally photocatalytic reduction. But metal complexes, because they have the higher good absorption and higher visible light activity, they can be used, but their homogeneous nature is the problem. So if we combine the both components, like we immobilize the homogeneous metal complexes on the suitable semiconducting supports, we can generate some hybrids or nanocomposites that can not only provide the recyclability and means recovery or recyclability of our system, but also increase the efficiency by taking participate in the electromobility as well as the charge separation process. So we based on our current research scenario, we are quite confident that such kind of the hybrid systems which consist the homogeneous metal complexes as well as the semiconducting supports can provide some solution for the real for the means solving this problem of the carbon dioxide for the conversion into the fuel or some valuable chemicals. But fundamental problems are similarly the main scale up is the problem of photocatalytic system, and another thing is the mechanism. We are not know we the mechanism of the photocatalytic systems is not so much known. So these are some fundamental problems. But in the future, we since hope we will work out, or we or our other research groups are working on this, and in the future something will definitely come out. So this is all about my work. Once again, I would like to thank you for all your kind attention as well as the organizers for giving me this opportunity. So thank you so much.
Thank you, Professor Sumanta Jane. Very nice and very different talks because we are heard about the different 2D materials or devices. So this is a real application to the 2D materials for societal application if we can really develop some efficient technology. So now it is open for the question session. So we can take some few questions.
Yeah.
Yes, I would like to know, ma'am, how much activation energy is required in this metal complexes for this photocatalytic activity overall for the reduction of CO2? So any typical range for the activation energy?
we have not measured the activation energy. In our system, we are using the 20-watt LED household bulb. So it's a very simple photoreactor that we designed in our means laboratory. By using this 20-watt LED bulb, and we are getting the activation of the kinetic part. We are working in collaboration with our sister laboratories. So in near future we'll have some this chemical engineering or kinetic part of these reactions.
Okay, ma'am. And another question: why this cobalt and this metal ion? How they benefit for on the graphene oxide surface? So how they benefit? How they give more beneficial for the graphene oxide photocatalytic activity? On the graphene oxide, you showed the cobalt ion.
No, these are not the cobalt ion. These are the cobalt metal complexes which are immobilized on the graphene oxide support. So cobalt actually it shows the binding with the CO2. So it increases the first of all for the most in most of the cases. The one is the major issue is the CO2 concentration in the system. So this cobalt bind with the CO2 and increase the concentration of carbon dioxide on this support. Another is that cobalt it can change its oxidation state, so it provides electrons to the graphene oxide, and those electrons on the graphene oxide can easily find the mobility on the unsaturated system, and they are easily available for the reduction of carbon dioxide. So by the combination of both the things, neither cobalt or nor that graphene oxide alone can work efficiently. However, their conjugates or their hybrid in the or we can say that it is the in combination they work better.
Okay, thank you.
Synergistic application, or we can say.
So, any more questions?
I have one question, Samaresh. This is Ankur here.
Okay, go ahead.
Yeah, so Dr. Jain is a very interesting talk, and it is very important also, the CO2 sequestration. I have a very general question in terms of like yield, whatever the material you are taking and the conversion, which seems to be very low. So in terms of the roadmap, what you as a kind of expert in this field, you believe that we can achieve, like where we are now, that in terms of the material usage and in terms of the conversion in extraordinary case, that is one. And the second is, once you use this catalysis, is there any possibility that you can reuse this catalysis, or it is completely useless after once you are conversion is done, completed? So, and the follow-up question of the previous speaker, that conversion time, how much time normally you can think of that this CO2, when it converts, you can get the methanol or any byproduct which can be useful, means like reasonable time which you can achieve, means conversion time, I mean. So yeah, if you can address.
Yeah, so I know the conversions are low, but if we look at the literature and in terms of comparison, if we see that these immobilized systems are providing much higher yield of the methanol from the CO2 in comparison. And another issue, I fully agree that the scale up of the photocatalytic reduction or photocatalytic experiments is a really challenge, because designing of photoreactor is a big challenge. Another thing is that all the systems are quite recoverable and reusable, and we have reused those systems up to 5 or 6 cycles, because we used a very quite lower amount of the systems like 50 mg or so and so forth. So the recovery of the 50 mg consistent recovery is a challenge, because some of the yield we get human error, or by the separation we get the lower recovery, but these systems are completely recoverable and reusable. And after the 6 cycles, we have all the characterization of these systems, all the morphology and all the bindings, everything is same. So we are very sure that these systems are not getting degraded under the photocatalytic conditions. But I fully agree that the conversions are low, and this is a challenge. But if we look at the science there, and we can work on it.
Okay, thank you.
If there is no more questions, let's once again thank the speakers for a very interesting and useful talk for this session. Thank you very much. So now we'll move to the next session, next invited talk. Our next invited talk will be given by Professor Krishna Balasubramanian from IIT Kanpur. So he did his PhD from Indian Institute of Science, and where he works on MOS2 and quantum well structure, mostly gallium nitride, aluminum gallium nitride, and then he worked as at Technion Israel Institute of Technology, and currently he is in Indian Institute of Technology Kanpur, where his research group is focusing on the interface of superconductors with low dimensional material for optoelectronics properties. He also work on the high temperature superconductor devices such as single photon detectors and nano inductors and tunnel super Schottky diodes. These single photon detectors and nano inductors are going to be useful for the future technology like the quantum information technology. So now we welcome Professor Krishna Balasubramanian for his talk, Valley Dichroism and Exciton Dynamics in Superconducting 2D Monolayers.
Thank you, Professor Das, for this kind introduction. And I'd like to thank the organizers of ICEE, Professor Das, Professor Ankur Goswami, for giving me this exceptional opportunity. I'm deeply humbled to talk in this forum of experts in this field from various places. My name is Krishna Balasubramanian, and I head the Nanoscale Electro-Optics and Superconductivity Group at IIT Kanpur, Electrical Engineering IIT Kanpur. For the purpose of this talk, I would like to talk about valley dichroism and exciton dynamics in 2D semiconductors and monolayers. The outline of this talk would be to develop an excitonic picture for 2D semiconductors. We have been seeing 2D semiconductors for about 2 days now. I guess not many people have spoken about the exciton behavior. I'd like to show the evidence for different excitonic species and show for the very first time some experiments regarding direct excitation of what is called as a dark excitonic state, and to measure its lifetime from dark to the bright excitonic states. There are some particular applications in quantum memories as well as terahertz generation. We will see as we go forward as to how they can be used. We have seen this particular table over and over again to the course of these 3 days. There are a bunch of 2D materials with various properties. It all started off with graphene, and then you have a bunch of materials which have properties very similar to graphene. You have graphene, graphene, hexagonal boron nitride, and then you have graphene oxide. You have 2D materials, particularly made of chalcogens. You have selenide, sulfur, tungsten sulfide, and zirconium telluride, and so on and so forth. And you have 2D oxides, bisco, copper oxides. They have superconducting behavior, as well as some perovskites and hydrides. So you have properties ranging from metals to semiconductors to wide bandgap oxides, as well as superconductivity. So you name a property, you can most likely find it in 2D materials. However, for the purpose of this talk, we are going to concentrate on some semiconductors which have specific properties with their bandgap aligned towards visible spectrum, and some range in the electromagnetic spectrum close to the visible light. So you have graphene and graphene, which has almost no bandgap. And then you have black phosphorus, whose bandgap is very close to the optical domain, but then it has some problem with the stabilities. You have dichalcogenides from tungsten, tin, lead, and so on. And then you have indium selenides, and you have boron nitride, which, as we spoke before, is a large bandgap semiconductor. But moly and tungsten dichalcogenides are particularly interesting because it's very easy to exfoliate, very similar to graphene, and they are room temperature stable. And there are some exciting properties, as we will see further on, which makes it interesting for photovoltaics and photo detection applications. So as we saw before, we are particularly interested in this particular materials, which of the form MX2. You have the moly material. So let's say, for example, moly disulfide. You have moly bonded to 2 sulfur atoms, forming this C3 or trigonal symmetry. And when you have these 2 pyramids, there are 2 ways to arrange them. One, they have 2 pyramids right on top of each other, forming the 2H phase, and then you have the 2 pyramids slightly twisted, forming the 1T phase. In the case of moly-based materials, the twisted materials are called 1T, have overlapping bands and hence have metallic character. But then the 2H phase, in which moly disulfide is mostly found, has this behavior which in the bulk has some sort of indirect band gap which occurs at the gamma point, and you can see that it requires an assistance of phonon to have excitation, and as you reduce the number of layers, you have the lowest conduction band move up in energy, revealing a direct band gap at the K point. And this is particularly important because this K has large wave vector values which determines some of the optical properties, as we'll see as we go forward. The band gap also changes significantly from about 1 eV in the indirect case to about 2 eV in the direct gap case. In addition to the band gap changing with the number of layers, you also have strong spin orbit interaction because you have heavy metals, and the heavy metals typically have electrons in d orbitals with L not equal to 0 and significant L value, so that you have L dot S giving you a spin orbit interaction, giving you a separation in the energy levels of the valence band. You have a lack of inversion symmetry because of the monolayer and even in odd number of layers, as well as the honoring of time reversal symmetry makes the band structure in the two inequivalent points in your Brillouin zone, the K and K prime points, to have the valence band to have opposite spins. For instance, if the topmost valence band in the K position has, let's say, have down spin, the topmost band in the K prime position have up spin, and the other way around if the other way is taken, right? So when we so basically we have this kind of a behavior in the valence band, but then the conduction band typically has these Z square metal atoms where L equal to 0, and hence you have very minimal or negligible spin orbit interaction or spin orbit induced splitting in the energy values of plus and minus spin in the conduction band. However, this is not just the case. The TMD materials have further tricks up its sleeve because of the fact that you have reduced dimensions in the Z plane. You have strong Coulomb interaction between the electrons and holes which are generated by, let's say a photon, and hence this leads to what is called as an exciton state. So you do not have single particle states, but then you have a quasi particle which has an interaction between the electron and hole which are strongly bound. The energy of the exciton states typically are lower than the free particle band gap by the exciton binding energy, which marks to be about 250 to 500 milli-electron volts, which makes the excitons room temperature stable. This can be compared against normal semiconductors whose exciton energies are about 20 or less than 20 milli-electron volts, which requires you to cool down these materials to see any excitonic behavior. In addition, this large spread in K vector values of these excitons also make these excitonic electron holes in these excitons spatially confined. This makes them similar to what is called as an hydrogen atom model, and hence these excitons are not the Frenkel kind of excitons which is typically seen in semiconductors, but then the Wannier kind of excitons which have particularly interesting optical selection rules and so on, as we will see further. Several experiments have been conducted on these 2D materials, and then two specific features are typically noted. For instance, in MOS2, you have two specific PL and reflection points at 627 nanometer and 670 nanometers. Experimentally, also you have the observed photoluminescence, which reduces in intensity as you increase the number of layers as well as the temperature. So these experiments typically follow the first principle studies as we have seen previously. However, an interesting turning point in these 2D materials and photoluminescence in 2D materials is the dichroism. So what we mean is that simple dipole selection rules dictate that because the valence bands are spin split, you have one kind of photon, that is right circular photon probably. Let's say, for example, right circular photon exciting the K valley, the left circular photon will automatically choose the K prime valley, and the other way around if you choose the other. So basically, this spin orbit splitting of the spin states in the valence band induces valley dichroism in these 2D materials, which makes it particularly interesting. So a dichroism of about 50% has been observed in these 2D materials, while in normal semiconductors about even 20% is very hard, and for doing this you have to induce some plasmonic effects and so on and so forth. However, this dichroism is not easily observed. you have to have a particular condition in which the valley dichroism is strong. So if you excite resonant or close to the excitonic position, you see strong dichroism as seen here, which is excited at 1.96 eV. However, if you excite at 2.33 eV, which is much farther away from the A exciton position, you see no observable dichroism. So which automatically kinds of hints at you that the excited quasi-particles in these 2D materials have very complex dynamics, so that if you excite much higher in energy in these 2D materials, you do not expect it to recombine quickly in the same valley, but then might probably jump away from the valley to the other inequivalent valley positions and so on. In addition to the valley dichroism, as we previously saw, you also see effects of the hydrogen series kind of level. So you have 1s, 2p, 3p, and all those things. So basically, you have increasing quantum numbers as well as the orbital angular momentum numbers. So basically, you have the s, p, d, and f states increasing with the angular momentum number. So you can, in principle, excite between these states as well as interband states using photons in these materials. These turn out because of the fact that you have hydrogen atom type of energy structures, which is brought about by very close electron hole spatial confinement in these materials. While all these things are well understood, you have the temperature dependent PL which throws a googly at you. What happens is, if you take the tungsten based materials and then the moly based materials and then cool it down, both of them, though similar in structure and similar in most of the characteristics with excitons, have really differing characteristics. So what happens in tungsten based materials is that when you cool down the temperature, the photoluminescence intensity drops. Whereas in the moly based materials, as you cool down, the photoluminescence intensity increases, which is typical in most semiconductors, right? So when you cool down a semiconductor, you have a higher photoluminescence yield because you are losing less number of excited carriers via phonons. But then for tungsten-based materials, is exactly opposite. So to understand this particular conundrum, so what was assumed is that you have what is called as dark exciton states or spin-forbidden exciton states. So what it means is, if I have a positive spin or spin up electron in the valence band, and if the lowest conduction band is spin down, we call this a dark state, because these two states cannot be excited by a single photon, because a single photon typically do not flip the spin. Whereas in the normal A case, because these spins are aligned, these can be, you can have exchange interactions using a single photon in this particular case. So you have a bright A state and you have a dark A state. Now, if we compare the conduction band energies in moly and tungsten, you can clearly see the difference, right? So in the tungsten-based materials, you can see that the bottommost conduction band is spin flipped, so that you have a dark state in the tungsten-based material. But then in the moly-based materials, you have some sort of a mixing. So this is on first principles. People have not clearly identified which one lies lower in the moly-based materials. There are there are a lot of contrasting experimental evidences for this. But then not all dark states are the same. That is, you don't have just spin forbidden dark states. There are a lot of forbidden dark states. For instance, when you form the exciton pair, if the electron jumps away from the valley, so you have a large K vector separation between the electron and hole, so you automatically have a dark excitonic state here. You have a second dark excitonic state which is spin forbidden, as we saw. You have a third dark excitonic state which have a different angular momentum. So let's say if you have an angular momentum 2 or 3, so basically that gives you another dimension for dark state which cannot recombine with single photon operations. Now that we see various kind of decay pathways as we saw, various kind of excitons as we saw previously, we have to also understand what sort of dynamics they play. So we understand that we have, let's say, an A series of excitons with multiple states based on the hydrogen atom series, and then the continuum. You also have the spin-flipped B exciton series, right? Now, if I put in a photon and then you have excitation up the conduction band, now this guy can drop down to the lowest excitonic state by what is called as thermalization process. And the exciton in the lowest state can recombine either via a defect level or can be scattered by momentum or by phonon in the same band itself, or it can recombine. Another way to do it is it can also be scattered to a different spin level valley or an inter valley, and then you form what is called as the momentum forbidden dark excitonic states. Now, with all these things, you have what is called as a radiative decay, you have trion formation, you have bi-exciton formation with different rates. So the question that we want to address here, and that's the purpose of the work that I have done, is that does the bright and the dark excitons exchange population? If they, what are the rates and what are these dynamics, and can we measure the lifetime directly? Now, why would I want to do this? Because as we saw previously in many talks before this, the the excitons in these 2D materials have particular applications in photo detection, in catalysis, as we saw previously, and in many places where you have light interactions. And when we have these dark excitons in these materials, you obviously exchange carriers and then you have the recombination pathways, which will degrade your performance. So it is obviously important to understand what sort of dynamics your excitons have once they get excited either by a photon or by doping. So to understand this, we have this kind of a setup. We have a very high-powered pulse laser, which goes through two parts. The first part goes through a OPA, where we can control the wavelength of the incidence. The second part goes through a sapphire plate, where we generate a white light continuum. Now, this is a very weak process, so you have a very weak white light source in the second part. And we have a delay stage, which can control the relative incidence times of the pump and the probe. We can measure via the spectrometer reflections from this sample, as well as whatever photoluminescence that came from this particular sample. Now that we show what exactly happens when there is a pump that is incidence on the sample, as we showed here. Let's say we have a pump which falls on the sample. All it changes is the carrier density, right? And what the carrier density changes is the subsequent absorbance of the probe pulse. And once the absorption is changed, it changes the real part of the dielectric constant via Kramer-Kronig integrals. And once K and N is known, you can calculate what is the reflectivity. So we actually did this experiment. We calculated what is the reflectivity. And then we show that very close to the exciton energy position, you have this waving nature on the reflectivity, which can be used as a measure for the carrier density, which got changed. And this is precisely what we did. So we measured the differential reflectivity versus wavelengths of the white light probe. So this is the reflectivity of the probe at various energies and the delay between the pump and the probe. So this tells that at 0 time delay, that is when the pump has arrived, and then as you go from the pump, if you delay the time of the probe, it can tell you what sort of carrier densities are present. So we typically get this kind of an exponential decay, which tells us that there are multiple decay pathways. This is a multi-exponential decay, and then we can fit our overall coupled equation to find different values. So what we do is we generate this kind of a coupled equation where there are several pathways which are known. One is the Auger exciton recombination, as we saw previously. You have trap-assisted recombination, you have radiative recombination, you have intervalley scattering, and you have spin flip scattering. If I include all of these things into the coupled equation and add the generation term, so basically you have both the bright and dark exciton population as well as the trap state which changes. With all of these things included, you have the final decay characteristics that we have to fit. And when we fit these things with this complete set of equations, we can extract the radiative lifetime. You can extract the exciton annihilation lifetime, trap-assisted annihilation, and spin flip scattering. So when we extracted these values, we find that the values are very close to what is typically reported for one photon or conventional excitons, so that it gives us confidence in the model that we are trying to fit. With this information, the proposal is, in the conventional case, we take an exciton, you excite to a continuum, let it fall down, and then you can measure these values. That's what we saw previously. But then what we can do is we can take an exciton and then excite it with sub-gap excitation. Now, the only way you can form an exciton is that you have such high intensities of the incident laser that you have 2 photon absorption. Now, first of all, we have to prove that we have 2 photon absorption. And when we have 2 photon absorption, it's obvious that the initial excitonic state and the final excitonic state should differ from twice orbital angular momentum, right? So basically, it is forbidden from single photon recombination. Now, for doing that, we measure the intensity of the photoluminescence versus the intensity of the laser which was excited. Obviously, the laser has sub-gap excitation. So we have excited from 0.951 and 1.13, where the PL position is about 2 eV. So when you have at 0.9 eV, it's obviously sub-gap even for 2 photon excitation. So you typically have no PL positions. And as you increase and go beyond this one, that is halfway mark of this band gap, then you start getting the PL intensities. Now, there are several other second order effects which can play, which is the second harmonic generation as well. But then when you change the energy of the excitation, we see that the peer positions does not change. It automatically gives you that you are having what is not a second harmonic generation, but two photon absorption. In addition, we also see that you have a saturable absorption characteristics in the sense that as I increase the intensity further, the actual intensity of the PL saturates, which gives us a feel that you are having what is called as a band bleaching, which will happen only when you have two photon absorption. Now that we have established that you clearly have two photon absorption, we can now study the dynamics. So here I'm plotting the similar, here I'm plotting the one photon dynamics that we saw previously, and I compare it to the two photon dynamics. There are marked differences. One is in the one photon case, you have a step change when the pump arrives, and then it slowly decays, which is normal, right? So basically, the pump changes the carrier density, and then it decays in the monotonic phase. But then in the two photon case, the pump arrives, and then you have a very slow rise, and then you have a decay of the excitons. Now, this is indicative of the fact that you have a producer-consumer kind of a relationship, and this can happen. Let us take in this particular situation where you have a two photon excitation to the 2p state, because now you have two photon excitation. So when you have something like this, you directly excite the 2p state, and the exciton has to fall down from the 2p state to the bright state. Remember, the probe pulse is a weak pulse, and then the weak pulse can only do one photon excitation, right? So basically, it is always only measuring the exciton density in the 1s state. So as you excite the 2p state, it has to now fall down, which causes the rise in the reflectivity slowly. But then once it starts populating the 1s state beyond a particular level, then the actual decay pathways take control, which gives you this non-monotonic decay. Now, once again, we can do the same exercise that we did previously. We can account for all sorts of dynamics and then solve this coupled equation. This gives you the exact numbers for 2p to bright excitonic state, that is 2p to 1s direct scattering lifetime. So we, for the first time, measured in a direct way the scattering rate from a 2p dark, that is angular momentum forbidden dark state, to a bright excitonic state, and which we found to be about 72 picoseconds. Now, this is not a very random number, because once you fit this into all the other data that you know, which tells us that most of the dynamics of excitons in these 2D materials falls in the range of about 75 to 150 picoseconds, because this is where the radiative recombination strongly dominates. Now, that is not all. So when we actually measure the pump probe reflectivity in two different conditions, that is, if I change the relative polarization of the pump and the probe, I see that I have an enhanced population when the pump and probe are opposite each other, which means that I have a stronger population in the valley which I did not populate. So if I take a right circular pump and then measure and put the probe to be the left circular one, so basically it means that I am populating with the pump the K valley. After some time, or almost immediately, I have larger population in the K prime valley. Now, that is only possible when we compare these particular situations. So I pump with two photon excitation, and then I directly populate the 2p state. And from the 2p state, it has to fall down to the 1s state. And that's what the probe can always measure, right? Now, it has several pathways. One, it can fall down to the 1s state, or it can scatter intervalley, and which we know for fact to be very, very, very strong. So because the intervalley scattering is extraordinarily strong, the 2p state, even before it falls onto the 1s state, gets scattered to the other valley and then drops down to this 1s state, giving you a stronger population in the valley which was not initially populated. So this gives you an interesting exciton dynamics when you measure the two photon excited angular momentum forbidden dark exciton dynamics. So with this, I close to show that there are different excitons in the TMGs. One is bright and one is dark, and then you can directly excite the dark exciton, which is optically forbidden to be excited. Typically, it is dipole forbidden by one photon pulse. That's why it's called dark. And you have an efficient intervalley scattering, which can make the valley which was not pumped to have a larger population than the valley which was pumped. And you have an anomalous circular dichroism when you have two photon excitation. Finally, I would like to leave this particular talk by this thought that we talked about decay from 2p to 1s. The only way this can happen is that it has to lose a unit of angular momentum, and that can be lost only by a photon in the most efficient way, and the energy separation is typically in terahertz. So this could be an ideal way in which you can pump a 2p state, let it fall down to the 1s state by emitting a terahertz. So this could be a way in which you can generate terahertz light by just normal optical photons with TMD materials. With that, I thank you for your attention and for the opportunity. And I'm open to questions. Thank you.
Thank you, Professor Krishna, for a very exciting talk on excitons. So now it's open for the questions. The question, we can take the question. Anybody has questions?
Yeah, can I ask one question?
Yes. Yeah.
Yeah, nice talk. So the one slide you show that W for WS2, while increasing the temperature, the PL peak intensity is decreasing.
Yes.
So is it so for other TMD? But I don't remember for the WS2 case. For WSC2 and for selenide case, it is also same or it is different?
So here you have for I think I'm getting an echo, but then nevertheless. So for all tungsten-based materials, you have a photoluminescence which increases with increasing temperature. That's because of the fact that you have a dark state below the bright state. So you need the thermal energy to excite a dark state from the, let's say, from the lower energy level to higher energy level for you to have photoluminescence. That's the reason why you have a photoluminescence which increases with temperature with tungsten-based materials. But however, it cannot be generalized. It is only known for, I think, only sulfur and selenide. One has to actually calculate what is the relative separation between the dark excitonic state and the bright excitonic states in the tungsten-based material. But typically here or in many first principle studies, they show that WX2, that is sulfur, selenide, and tellurium, for all these three, you have the dark state lower than the bright state.
Okay, thank you. I will check that. Okay.
Any more questions?
Somebody has asked question in the chat box. Can you?
Yes. So, what is the significance of the different time constant in the decay profile, like MOS2, WS2 in PL and ultra fast spectroscopy? And what is the significance of the average value of the tau?
So the tau determines the active lifetime of any of the excited particles. So it gives us, let's say, if you're looking for photo detection application, you typically want the lifetime to be really, really large. So that if you have a photo excited excitons, you want them to live longer than they transfer to the context, right? If you have a really short lifetime, it will probably decay even before it reaches the terminals for you to have any accountable current. So it depends upon the application that you're looking at. If you're looking at, let's say, photoluminescence or luminescence applications, you typically want the radiative lifetime to be much shorter or to be the most dominant recombination pathway. But then if you want photo detection applications, you would want the lifetime to be much longer so that you have an additional current for every incident photon, or you have a higher quantum yield, so to speak.
So I have one question.
Sure.
So in the, like, you did not talk about that things, but that is interesting, obviously, the terahertz emission. So for that, to take the terahertz emission, the lifetime has to be very fast, like very small in the sense. Am I right?
Yes, you are right, exactly. So basically the lifetime, I will just go to that particular. So if I really need to get terahertz from this, the lifetime for 2p to 1s has to be really fast in comparison to all other lifetimes. So the 2p excited exciton can also recombine by any other process like Auger or defect or any other process, right? So it just cannot have radiative recombination, but it just can be phonon scattered to intravalley and then have several other multi-phonon scattering processes and such. As you rightly pointed out, it depends upon what is the rate at which this guy falls from 2p to the 1s state. If that is the shortest lifetime, it will be the most dominant process, giving you probably the largest yield of terahertz radiation.
So do you have an idea like which 2D materials will be like, I don't know, like good for this terahertz emitter, like using this?
No, sorry. So basically, this is so we have been able to do this measurement only on the MOS2 ones. So we have value for about 72 picoseconds for MOS2, but we have no other information of other materials. It is not yet reported.
Yeah. Okay.
I have one query, Samaresh. This Krishna.
Yeah.
I just missed some part
Sure.
regarding the quality of the film, how it matters. I believe because this, as you told, this exciton when these decay things are happening,
Right.
there is a possibility of recombination or any other non-radiative decays. So,
Right.
in terms of the quality of the film, how can you ensure that this will be this may not be the case? So, I might have missed actually because
No,
how
sure.
to
I mean, I think it's a relevant question. So, the quality. So, we have just tested with exfoliated samples. So we do not know the exact nature of defects. But then, any of the defect which is present in the material and which is particularly sub-gap energy defects, it will always contribute to higher recombination rates. So, if I have a defect like this in this particular fashion, in addition to the radiative recombination, I will also have defect-assisted recombination, which will be very, very effective, depending upon the density of defects. So there cannot be, I cannot give you one single answer for this. But then, if we have a lot of defects, we can expect many of them to lie in the sub-gap region, and they are anyway bound to be, let's say, affect your yield in the negative fashion.
Okay. So the pristine, high quality film is necessary for this.
Definitely. Yeah. I mean, it will be. I mean, as in any semiconductor, right? So basically, you would like to have a good quality semiconductor to have reasonable radiative yields, so to speak, as well as lifetimes. If there are, I can stop. Thank you.
Yeah. So if there are no more questions, once again, thanks to the speaker, Professor Krishna, for a nice, exciting talk. Thank you, Professor Krishna. So
thank you.
Now we'll move. Okay, thank you. So now we'll move to the next contributory presentation by Sumit Sharma. So he will be talking about the platinum diselenide thin film based field effect transistor for ammonia detection. Sumit, are you there?
Yes, sir.
Can you share the screen and try to finish with 10 to 12 minutes? Then we'll have some few time for question and answer.
Okay, sir. So good afternoon to all of you. I am Sumit Sharma. First, I would like to thank to ICEE Organizing Committee to giving me this opportunity to present my work as a oral presentation in this ICEE conference. The title of my talk is Platinum Diselenide Thin Film Based Field Effect Transistor for Ammonia Detection. The contributor of my talk are Dr. Akshay Mudgil, Professor Prashant Misra, and Dr. Samresh Das. The outline of my talk is a brief introduction about gas sensors and synthesis of PTSE2 and field effect transistor fabrication, structural characterization of PTSE2 thin film, FET characterization, and ammonia sensing. Then conclusion. Introduction. The sensing of gas molecule is critical for environmental monitoring and control of chemical processes and medical application. The detection of these gases like NOx, CO, NH3 is very important. The NH3 is mostly produced by the pharmaceutical industry and agriculture fertilizer manufacturing industries. The detection of this gas is also important for industrial safety and safe storage and transportation of food and agriculture products. Here we are particularly targeting ammonia gas because more than 30 ppm of ammonia exposure has severe effect on human organ, and it is well reported by WHO. The more than 5 micromolar concentration of ammonia in human blood lead to the improper functioning of kidney that leads to the disease called liver cirrhosis. So from different available technique, the metal oxide based gas sensor are widely used and most popular. But the problem associated with this kind of sensor, their they are operating at higher temperature. For some application, this higher temperature operation is not feasible, and that higher temperature operation is also leads to higher power consumption. So here in this work, I am using field effect transistor as a sensing device. In this field effect transistor based devices, the sensing material is used as channel layer between source and drain contact. The most important advantage of this field effect based device, their higher sensitivity, their real time detection. So for different available sensing material, nowadays 2D material are most popular and most favorable choice, because due to their advantage of higher surface to volume ratio and their tunable band gap. But the most important advantage associated with this 2D material, their room temperature operation, that leads to fabricate room temperature device and for room temperature operation. So here I used PTSE2 as a sensing material. So for PTSE2 synthesis, first I deposit PT thin film over SiO2 substrate by RF sputtering. The thickness of PT film is 5 nanometer, and the salinization is performed in 3-zone furnace by keeping this PT deposited substrate at middle zone at 500 degrees C, and salinization for salinization, selenium powder is placed at zone 3 at 200 degrees centigrade. The carrier gas is used here are mixture of hydrogen and nitrogen at constant flow of 100 SSCM. And the device fabrication flow is started with this thin film deposition of this PTSE2. Then channel is patterned by optical lithography. Then source drain contact metallization is performed by optical lithography and chrome gold deposition by sputtering. Here figure A shows the same micrograph of our channel region, and inside figure shows the PTSE2 nanostructure. Figure B, here figure B shows the schematic of our fabricated device in backgated configuration. Here we use 300 nanometer thermally grown oxide as a dielectric, and figure C shows the batch processing fabricated device on 2-inch wafer. Here channel length of our device is 5 micron and width is 10 micron. To confirm the formation of PTSE2, we did different characterization for PTSE2 thin film. So figure A shows the Raman characterization or Raman spectra of PTSE2 thin film. Here peak at 176 and 106 shows the in plane and out of plane moving of SE atom. From this XID characterization, we got different available plane in our PTSE2 thin film. The next characterization was a study of XPS spectra that confirms the presence of PT and SE in our PTSE2 thin film. For again, different characterization was performed by energy dispersive X-ray diffraxometer that confirms the presence of platinum and selenide in our PTSE2 thin film. For device characterization, we used SCS 4200 parameter analyzer in our lab. Figure A shows the output characteristic of our device for different gate bias, and figure B shows the transfer characteristic of our device for fixed drain bias of 2 volt. From this transfer characteristic, we got some important parameter for FET device like threshold voltage, field effect mobility, and substrate swing. For the threshold voltage of our device is 1.6 volt, and we got field effect mobility of 5.42 centimeter square volts per volt second for our device. The gas sensing performance of our device is tested in-house developed a gas sensing setup where we first purge our device with N2 to stabilize the current of our device. Then different concentration of ammonia is purged in our sensing setup to check the performance of our device. Here, this figure represents the device response for different concentration of ammonia gas. For our device, the rise time is 140 second and fall time is 150 second. That is quite large, but it is comparable to available literature. But the most important advantage of our device is we operated our device at room temperature for ammonia sensing. Our target, our main target for this device is used is for biological application. For that, we characterize our device with PBS and ammonia. PBS stands for phosphate buffer saline. So we prepare different concentration of 10 to 30 micromolar of ammonia in PBS and characterize our device for real-time application. So in future, for future application of our device, we are targeting detection of ammonia in human blood. Here, figure B represent the different device response for different concentration of ammonia gas. Here we first characterize our device with ammonia gas to validate our result that our device is showing response for ammonia gas. Then we will characterize our device for PBS and ammonia. So here figure B represent the our device performance for ammonia gas from 5 to 50 ppm concentration of gas. So our device shows good sensitivity for a 5 to 50 ppm concentration range of ammonia gas. Here are the comparison table for different available 2D material based and metal oxide based sensors for ammonia gas detection. So our device responded very well at room temperature operation. At last, I would conclude my talk. So our device is showing very good response for ammonia gas, and our device is showing very high responsibility from 5 to 50 ppm ammonia gas, and our device is also compatible for liquid ammonia detection like blood ammonia detection for real-time and point of care application of human health monitoring. So at the end, I would like to thank to Nanoscale Research Facility, IIT Delhi, Ministry of Electronics and Information Technology, and my professor, Dr. Samresh Das, and Professor Prashant Misra, and microelectronic group member. Thank you.
So thank you, Sumit, for timely finish the talk. So now it's open for the question. We can take few questions.
Sumit, this is Ankur here. I have one question regarding your this
Yes,
response profile of the
Yes.
ammonia. Could you
Yes,
go
sir.
to the screen? I'm not able to see the.
Okay.
Can you share the screen and show that?
Yes, sir. Yes. This
Slide
one?
number 14. Yeah. So some discrepancy here. What I look in like the time response, it is not saturating for the other two peaks or the other two response. The first
Yes, sir.
one.
Yes, sir. These are the very initial result of our device. We are
Okay.
further optimizing our device. So our next target is for plasma as well. So these are the very initial result of our device.
So these are all room. Okay, go ahead, please.
So this result is for the liquid or gas phase in the ammonia?
Sir, this result for liquid.
So ammonia is in PBS solution. So
Yes,
it is
sir.
like
Ammonium hydroxide in PBS for different concentration, like from 10 micromolar to 30 micromolar.
Okay.
So if
because,
we compare it with, yes,
no,
sir.
no, because you have to understand, because when you are putting ammonium hydroxide in PBS, it will take some time to form the ammonia gas also. I don't know which reaction takes place to form the ammonia using this ammonium hydroxide. You have to look for those things also.
Correct. So in that context, is it are you dipping like dropping this liquid in the sensor?
Yes, sir. Yeah,
Is
channel
that the way?
surface. Yes.
Okay. Oh, and that's why it is so high. Okay.
So we are dropping 4 microliter of this PBS ammonia solution on our channel surface. Then after that, we are washing our surface with DI.
Okay, and all are in room temperature basically.
Yes.
The measurements
Yes,
are.
sir. Yes, sir.
Oh, thanks.
Any more questions? So if there are no questions, so we are concluding our session. We have two talks, invited talks, one from Professor Himan Lata Jain and one is from Professor Krishna. So one is for the CO2 reduction. So that is important for the societal like for current situation. And Professor Krishna is given a nice talk on excitons for future, like it can be used for different quantum or other also terahertz device application if you clearly understand the excitonic physics on these 2D materials. And the last is on the ammonia gas sensor in human blood, if you want to say. So thank you, all the speaker and all the participants who are attending this session. Thank you. Now I'm hand over to Professor Onkul for the.
Yeah, thank you, Samaresh. It was a very exciting for the last 3 days. So it was kind of a different platform which we have actually first time encountering. So, but as an experience of these last 3 days, I think we have done it pretty well. And this is also a very great opportunity for us to conduct this kind of manage this kind of conferences in future if these things persist. But I do believe that we'll be in the better time in the next forthcoming months. So I think we are hoping that we will meet again in the next conferences. And the upcoming conference is IWPSD organizing by IIT Delhi in the next year. So I am inviting you all in the December 2021 with SSPL. So thanks a lot again for joining this, and wish you all the best and stay safe. Thanks a lot. So with that I conclude.
We have a, like there will be one session for the all the session together for announcement for the conclusion session. So all the participants are requested, and there they will announce the poster award and other conclusions. Okay.
Okay. Yeah.
So all the participants are requested to attend that concluding session.
That is on 5, I think 5 o'clock, right? As a time.
Yes, I
Okay.
think so.
Okay.
I cannot know.
Okay. Thanks a lot. Okay.
Okay, you can check the Icee website for that. Thank you all.
Hello, sir. Hello. 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 Hello.
Okay, so actually we are here for the poster review, right?
Yes, sir. Sir, can you hear me?
Yes, yes. Okay, so
Sir,
let's
actually,
wait. Yeah.
sir, actually, my poster is not presented yet. That was the on 26th. So this is the time. So can I? Because there is a actually there is a class of mine. So if you will tell, then I can start my poster presentation.
Oh, actually, there are one or two more people also there. So let's wait for 1 or 2 more minutes.
Okay, sure.
And we have to start at so maybe you can start first. Actually, that is
Yeah,
not a
yeah,
problem.
yeah. Thank you, sir. Thank you.
Okay, Vineet, can you share your poster?
It seemed to you?
No. Yes, yes, yes. Just wait for. Just wait
Pushparaj,
for. Yeah. Yes.
Dhiman here.
Yeah.
So what I'm saying, maybe we can start with some other poster and let Bhaskar join in, then we can go through this.
Okay. So basically, so Bhaskar is still not here. So what we can do is, if any student from Bhaskar is there, then he can present first, right?
Right.
Okay.
Okay. So any student under Bhaskar Mitra is here?
Hello, sir. I'm here. I'm Satish. Can I present, sir?
Yes, please go on.
Yeah.
Audible, clear.
Yes, yes.
Okay, sir. I'm sharing my screen. Sir, my screen is visible, sir. Hello, sir.
Just wait, just wait. I think last time was yes, yes, it's fine. So,
Yes, sir.
Satish, you have only 2 minutes to present. Okay,
Okay, sir. Okay.
please go
May I
ahead.
start? Okay. Good afternoon, everybody. So, I'm Satish, and I'm presenting our work on spin softening and damping effects on in thin dielectric MEMS resonators. So, basically, in that, our objective was to quantify the damping effects and quality factor in a MEMS resonator, and also see the frequency tunability in MEMS resonator. So we choose a fixed beam in MEMS resonator. In that we have a drive electrode and a sense electrode. We are using internal dielectric transduction because of some advantages, like it has a very low impedance and low motional impedance, and electrostatic coupling is very high in that, compared to the air gap resonators. So if you see the basic model of our structure, we have a fixed beam with a thin dielectric. Here we are taking a high K dielectric of hafnium oxide, and we have electrode for sense and for both drive and sense electrodes also. This table presents the specification of the our simulated device. So basically, spring softening effects are coming basically spring stiffness in this device has a mechanical stiffness due to beam and electrostatic stiffness due to electrostatic force, and also one stiffness is coming because of a thin dielectric layer on this resonator. This layer has a stress, and this stress has a quadratic voltage dependent on DC voltage dependent, which changes the whole device stiffness, and because of that the resonant frequency of the device changes. So, and we are also calculating damping effects in this structure because of basically we are taking the dominant effects, damping effects like anchor losses and also thermoelastic damping. So for modeling the thermal anchor losses, we have taken a perfectly matched layer at both fixed ends, and to model a very large substrate, and so to model the acoustic radiations from the substrate to the structures. So if we go in the result, so we can see that due to high dielectric, because in internal dielectric transduction, this parameters like electrostatic couplings and impedances depends on the dielectric constants. And if we choose a high dielectric with very thin, so we have advantage like we get a very high like high deflection sensitivity as well as capacitive sensitivity. We are from the results we can see that also we are seeing that we are getting very high coupling efficiency, and in frequency tuning we are getting a quadratic dependent of frequency deviation, resonant frequency deviation due to DC bias voltage. And we can see that due to high dielectric we are getting a strong control of resonant frequency due to high dielectric. So we can tune this we can use this in frequency tuning and also correction way of due to fabrication process deviation in resonant frequency in resonators when you are using a device for filter application or any frequency sensitive device application. And also we simulated for the resonant frequency with temperature to see how it's affect, and we are seeing it's a very less it's almost stable frequency with coefficient of 0.19 ppm per volt. This uh, this this model shows the modes structure due to anchor loss, and we are getting overall anchor loss overall quality factor due to anchor loss and thermoelastic damping is around 1300. Like we have very less high quality factor due to thermal elastic damping, but anchor loss is very dominant in this structure. This device is in fabrication process. It is in process. We are in final stage and trying to release the device, so we can see a final microscopic image of this device. So we have a drive pad, we have a sense pad and this beam structure, and we have a driving electrode and sensing electrode. But these two images are showing the some optimization process in the process. So now this device has to be characterized and after the fabrication. Thank you, sir.
Okay, so I don't have any questions. So because we are running really late actually. So Dhiman, do you want to ask anything quickly?
Among the thermoelastic damping and the anchor loss, so how do you determine, like how do you characterize these losses?
So anchor losses in the model we have, I used the COMSOL simulation model, sir. So in that I have defined a perfectly matched layer, very thin, perfectly matched layer at the both end of the beam, at fixed end of the beam, and then I model for anchor losses. So we are getting a damping and by mode shape modeling, eigenfrequency modeling.
Okay.
And for this thermoelastic damping, we have a thermoelastic elasticity physics in the modeling of COMSOL, and then we directly model by anchor modeling, eigenfrequency modeling. Yes, sir.
Okay. I don't have any further question.
Okay, so can you go to the next one quickly? So maybe now Bhaskar is also here. So what you suggest, like we go one by one, by number, or how should we proceed?
Yeah, we should go by number by number. All
Okay,
three
so
of us are here.
Yeah, so basically poster number 113 is here. So those who has presented yesterday, then you can skip actually. So 113, because today we are only having people who did not present on 26. So
Yes, sir. Yeah, my
113.
name is Shubham Saxena. Good afternoon.
What is your poster number?
113.
Okay, can you share your screen? You have not presented on 26?
No.
Okay, please go ahead. You have 2 minutes to explain.
Satish, just wait for a minute, and you have 2 minutes to present your work.
Okay, we can see your screen. Please go ahead.
Subham,
Hello.
I think there is some problem with your mic. There is lot of echo.
so Subham, if you are logging from the multiple places like app or web page, just use any one, please. So just check your microphone or earphone, whatever accessories you are using, please. Not exactly. Say something. No. Still, we are receiving the interrupted voice. Is it like that, Professor Pushpas?
Yes. It's a
So
problem actually. So
yeah.
maybe we can have you later actually. We can go to the next poster. You please log off and log in again. That will be better. So
One
next one is.
Sir, sorry for the interrupt. One more announcement for the Rising Zima. Please log out from the multiple places, please. I'm able to see you are logging from the multiple places. Thank you.
Okay, because others can also create this ego issue actually. Okay, so we can go to the 114 is done already or not? 114.
Sir, actually we don't have the data, so it's better to call one by one by the number series,
Yeah,
I
so
think.
I'm calling 114 is done. So if not there,
114 is done. 114 was done on the 26th.
okay, 115.
Yes,
Yes,
sir,
sir.
done.
115. I have presented already.
115 is also done.
Okay, 116.
That is also done, I think.
Okay, 117.
So 117, I don't think is present.
Okay, so 118.
118
Yes,
we
sir.
just finished.
Yes, sir.
Okay, 119.
119 was
done.
Okay, 120.
Finish.
120 was done
Okay,
yesterday.
120.
121 I think is what we need to do.
121.
Power. Shubham Power, but he is not there in the participant.
Okay, so we go to 122.
122 Faizan Tariq Beg.
He is also not there.
Okay, so 123.
123 I think
It is done.
it is done yesterday.
Okay, so 124.
Yes, sir.
Okay, can you? 124. Okay.
Yes.
Hello.
Yes, we can see a black screen. We can't see your screen.
Yeah, just wait. I think it takes some time.
Yeah,
actually.
is it about to come, sir?
Just wait. So it is for all the poster people. Please, finish your explanation in within 2 minutes. So we are running really out of time. Oh, I think his poster is still not there.
Not exactly, Vinith.
Can you share again, maybe?
No.
Vinith, it is still black screen is.
Please read that, sir.
Still, your slides are not visible to us.
Okay.
Poster number is 124, right?
124.
124.
Poster number.
No, we cannot see the slide actually. So Vinith, maybe what you do is you log off actually, and maybe we go to 125 first, and then we come back to you. You log off and log on again.
Okay, okay.
So, poster number 125 can start, sir?
Yes, please.
Sir, are you able to see my slides?
We can see your screen.
Your screen is there.
Okay.
Can you open the?
Yeah. Now I think it's perfect. Is it okay, sir?
Yes.
Yeah. Please explain very quickly within 2 minutes.
Yeah. Okay, thank you. So this is Sushil Kumar here, a PhD student in Professor Puspara Singh Group at IT Delhi. So in this work, particularly we have examined the operational mode as well as the temperature range for to characterize NEMS relay switches. So the idea was to people uses the hysteresis voltage as a negative remark, because the longer hysteresis voltage causes the stiction, which is damage the permanently the switching operation in the switch. So we have examined the hysteresis voltage and we try to modify its numerical value by using the operational mode as a designing tool. So the simple idea was in electrostatic switches, like in the rightmost diagram, we can see there is the two gap in the typical cantilever based switches. One is the actuation and second is the contact gap. And usually the actuation gap usually have the larger value than contact gap. According to the literature, if we take the ratio of this gap in such a manner that before the coming to the turning into the pull-in instability region, if the Icee is put in such a that the suspended electrode touches the drain to turn on the device, so we will define a new operation region in that scenario, which is called NPI, non-pull-in region. So we have examined the hysteresis voltage for in that scenario, and we also found that hysteresis voltage have a very extreme application in the digital IC design. Like it indirectly decides the power consumption in the circuits. And for the logic relay operation, it should be very finite of value. And for the memory application, it's large, but it should be repeatable. So that we chosen the hysteresis voltage for the design variable in this work. And we have, apart from the mathematical or console modulation, a simulation, we tested a very standard terminal cantilever structure, and we characterize it for start from the room temperature to higher temperature. So since I already told the ratio of the both the gaps is very critical here, which decides the operation range. For pull-in range, the air gap, the contact air gap should be greater than 0.3 times of the actuation gap. However, for the non-pulling gap, for the non-pulling operation, it should be lesser than 0.3 value. For the CMOS compatible fabrication process, we found that the ratio of the air gaps in the fabricated device is lies in the pull-in region, and we have characterized the device, and we found a value of around 2.7 volt in the leftmost diagram of IV characteristics of the hysteresis voltage. And since our ultimate goal was to investigate the variation of hysteresis voltage with temperature, so we have characterized the variation of the hysteresis voltage in the figure 3. And we found that the hysteresis voltage is directly proportional to operating temperature, and it keep increasing with the temperature. So indirectly, the uniqueness or the key outcome of this central graph is that we quite familiar with the pulling voltage variation with the temperatures, but there is a very rare reports on the pull-out voltages, means when the device is about to detach from its contact position. And the key point here is the pull-in, as usual, the pull-in voltage is independent of adhesion voltage. However, the detachment process, which is typically called pull-out operation, is highly depends on hysteresis voltage, and that is why the adhesion force. So here we signify the hysteresis voltage, or it's better to say adhesion voltage is increasing here with the temperature. Since we have examined this configuration of the moly to moly contact, we have used the molybdenum as a contact or as a structure layer, and we found the temperature. With the temperature, both the adhesion and hysteresis voltage increases, or in other words, we say the releasing voltage or pull-out voltage is decreasing with temperature, which somehow indirectly signifies there is the huge adhesion forces present between the contacts. And the figure 4 signifies the variation in the pulling voltage, which is already matched with the results, which is directly decreases significantly for the short cantilever configuration. And for the longer configuration, it is decreases too, but the rate of decrement is quite slow here. So this is the ultimate outcome was to investigate the effect of operation voltage and temperature on hysteresis voltage. So this is the from my side. Thank you.
Okay. So I have a quick question. So you showed the results for non-pull-in devices, the temperature dependence. What about the pull-in devices? Are they similar?
Sir, exactly. These measurements results are for the pull-in devices. As I told, the ratio should be very critical here. So after the fabrication, because of the residual stresses, we found our gap ratio landed to pull-in region. So this, whatever experimental result we have showed here, this is for the pull-in measurement. But our analytical
any difference between pull-in and non-pull-in? I don't. I don't expect a difference between pull-in and non-pull-in, right?
Right. But sir, our analytical models which calculate the hysteresis as well as the pulling voltage tell us, which is not shown in this particularly work here. We found a significant difference in this hysteresis voltage because of the change in pulling voltage, or maybe more accurately turn-on voltage.
Okay, so because of that, okay, yeah.
Right, sir.
Yeah, no, I got it. Okay, Dhiman, any questions?
No question. Maybe next poster.
Okay, so we can go to the next one actually. So next one is 127, right? So actually 126, I did not get it. So is there any poster for 126?
No, I don't. So if he is not here, we skip, I think.
Okay, 127, please.
127 is Ankur Saxena.
Yes, sir. Yes, sir.
Can you share?
Please. Yeah, please start.
Yes, sir.
Ankur, you please start actually.
Yeah. Good afternoon, sir. This is Ankur Saxena. I have working on a integrated pressure sensing layer in the macro channel for microfluidic applications. So I have designed some cantilever in a micro channel devices, and in which where I have like velocity and pressure I have studied about. So what I have to design, it is very difficult to design to pressure sensor and directly to in any macro channel, because the size of a pressure sensor is in millimeter, and it is very difficult
Ankur,
to
maybe you need to zoom in particular block because I can't hardly see anything.
Yes, sir. Is it visible, sir?
Yes, better now.
Actually,
Okay, maybe you can go to your device structure. Then it will be easy for others to understand.
Yes, sir.
Yes.
So
Yes,
this
here.
one is I have worked on a console multi-basic software, and I have designed some micro channel devices in which cantilever are integrated, and this cantilever is designed by like two type of material I'm using, like PDMS and parallel materials, and study of these both of the material properties by applying fluid flow on the micro channels. So I put cantilever on the inlet. That one on the inlet side, that is present on the most and left. Hello. Hello.
Okay, so Ankur, maybe can you hear me?
Yes, sir.
Okay, so no problem. Basically, so maybe I can ask the question based on your because I opened this. So usually we have pressure sensors actually either absolute pressure sensor or maybe we have reference pressure sensors. So what is the reference pressure in your case?
Yeah, actually, I work on the some activities on the pressure sensing layer. I have to create. I am not insert directly to pressure sensor in any macro channel. So I work on like a
But
PDMS.
for the pressure, you should have some reference pressure also, right? With respect to what? So in the macro channel, how will you create a reference pressure?
So I use the material of the PDMS materials to create a for the as a reference material. Like PDMS, Gallium, they are the material work as a pressure sensors.
Okay, so anybody else has any question, please?
No.
We can go to the next one then. Is fine. So thank you, Ankur. You can start sharing.
Thank you,
So may I check again? 124.
124. Yeah. Okay. Okay.
So now.
Actually, it's still not there. I don't know why.
Okay, I can see we can ask questions based on the poster. We can look at the poster separately.
Okay.
And probably ask questions. I think that may be a better way to go. Okay.
Okay. Yeah.
So may I present, sir?
Oh yeah. Now we can see.
Okay, you can see now.
Yeah,
Yeah,
your
we
voice
can
is
see
also
now.
clear. So go ahead, please.
Okay, sir. Good afternoon, sir. And I'm going to describe the effect of micropattern magnet in microfluidic channel over bulk magnet. Actually, the main aspect of microfluidic based device is to separate or capture the particle in microfluidic devices. But here, if we can see that there are a lot of advantages if we are using the micropattern magnet, because if you are seeing the COMSOL simulation in result sections, then we can see that the intensity which is high only at the edges of the magnet, which is clearly seen in the bulk magnet in the figure B. And if you are using the micro pattern magnet, then at each and every edges there is a high intensity magnetic field can be seen. And this intensity which is seen here in the micromagnet is also responsible for the finding the gradient of magnetic field. Here the gradient of magnetic field is also playing an important role in finding the force, because the force on exerted force on the particle is proportional to the gradient of the magnetic field. Here we can see here we can also see the device research challenge. In that particular challenge, micromagnet and optimum gap density. If we decrease the gap whenever micromagnet is called decreasing the WG, and when it comes close to 60 micrometer and towards lower to 60 micrometer, then it is very challenging to fabricate the particular integration. So here the main here if we can integrate it to the up to the 20 micrometer, then we can capture more and more magnetic field gradient. And if we can capture more magnetic field gradient, then the effect on the particle will be more, which can be seen from that formula, which is Fm equals to mu naught Pp chi mp divided by chi mp plus 3 and gradient of the fields. Here chi mp is the magnetic volume susceptibility and Vp is the volume of the particle, mu naught is the magnetic permeability of the space. The main aspect is of the micromagnet. Here we can see in the effect of parametric variation on average magnetic field intensity. We can see that in at the edges here we can see the sharp intensity. So this type of sharp intensity can be also used, like if in a fluid there are two types of fluid, and if we have to mix, then due to this type of jerk, that particular fluid can be also mixed. And even if you are using different shape of the particle, then if any particle is stuck at any point, and if you are using the micromagnet, so due to this particular jerk at a particular intensity, it provides some acceleration, so so that any stuck particle can be come across to in the micromagnet. So here magnet over the bulk magnet, even still using the bulk micromagnet, because the pattern micromagnet is very difficult to fabricate with the optimum distance. So here the gap distance is Wg equals to 20 micrometer and G equals to 20 micrometer, reflecting the highest peak intensity in the channel. Even here for bulk and pattern micromagnet records the maximum field intensity of 290 kiloampere per meter and 204 kiloampere per meter respectively at the edge of microfluidic channel. Here the main conclusion is the micro scale magnet induce local magnetic forces on magnetic particle to achieve continuous separation of microparticles. Further improvement in the device performance pattern of
Okay. So we seem to.
Hello.
Okay, Vineet.
Yes.
Okay.
I
Yeah.
think we asked questions on this, whatever.
Okay, so Vineet, I have a question. So, you mentioned about the micro scale magnets, right? So,
Yes, sir.
what material and how you really make it actually,
Sir, actually, I am using the rare earth magnet because I have to make a more effective BH maximum.
No, are you planning to fabricate this for your micro channel or how it is?
Sir, firstly, I am simulating. After I'm going to fabricate it, and after which one is the gives the better result, and then I will go for that fabrication part.
So how will you fabricate a rare earth magnet on chip?
No, sir. Actually, I am purchasing the powder of that rare earth magnet, and after taking that powder, I will use the Dr. Blade technique. In that particular technique, I have to take like silicon wafer, and I will etch that particular thickness, and after that, I have to pour that magnet, and then I have to take something for putting into that sticking on that wafer with that material powder magnet like NdFeB. So, sir, using Dr. Blade technique, we can fabricate this.
Okay. Question about your simulation.
Yes,
Won't you get a better field gradient if instead of square pillars you had more, say a triangle shape where your magnet is,
Yes, sir. Yes, sir. Actually, sir,
this
in
particular.
triangle. Yes, sir. In triangular magnet, yes, I have seen that the force which is coming out is not covering a lot of area. Like here, if I am using the rectangular magnet, then it will capture a lot of area and it will influence more and more onto the particle. But if I am using only triangle, then it will give the intensity definitely. But if I am talking about the force,
Right.
too much.
Okay. Okay, that's fine. Okay, I think we can move to the next one. So next was paper number 128.
Yes, sir. I'm
Can you
just
share
sharing.
your?
Yeah.
Beneath, please stop the sharing of your screen, please.
Sir, is it visible?
Yeah.
So, I'm Mahesh Kumar and I'm working in FlexMem Research Center, Manipal University, Jaipur. So, in this work, I will be presenting the phenomena where the levitation of red blood cells in the microchannel will be taking place. This phenomena is used in microfluidic MEMS device applications, which are applicable for separation of biological cells. So in this work, I have done some preliminary analysis on a microchannel where we are having coplanar electrodes. is it like, sir, you can see this channel?
Yes, we can see. Continue.
Yeah, so there in the blue color you can see that there are 9 electrode gaps. There are total 10 number of electrodes. In between there are 9 electrode gaps, and these electrode gaps are excited with some particular voltage, that is 5 volt, and at 100 kilohertz frequency we are creating an electric field gradient. The gradient in the electrodes are on the bottom floor of the channel, so gradient covering up at particular height of the channel, up to the height of the channel. And then we are inserting red blood cells. The properties of the red blood cells are such as that it shows negative dielectrophoresis, because the polarizability of the red blood cell is lesser than the fluid polarizability. So when the property dielectric permittivity of the cell is less than the fluid dielectric permittivity, then cell experience a negative dielectrophoretic force. This negative dielectrophoretic force means that the cells will go away from the strong electric field, means it will attract towards the weaker electric field region. So in electric field distribution, figure number 2, you can see that there is an electric field distribution where at the bottom floor of the channel near the electrodes, electric field is very high, and at the top floor, like at the top positions, the electric field is very low. So that means red blood cell will tend to levitate. So due to it will get attracted in the weaker electric field, and the levitation of the red blood cells will take place. Here at in figure 4, we can see that the figure A shows that velocity profile of the channel, and then in figure B, what we have done, that we have taken the trajectory how the cells is like levitating at different velocities. So from 200 micrometer per second to 350 micrometers per second, we have observed that red blood cells can be levitated successfully, and red blood cells are levitating in the microchannel. And in figure 4D, the trajectories are shown. So we can see that at inlet side, at multiple, the position was the suspending position of the cell was random. At the end of the channel, at the near the outlet, all the cells are levitated. So like we can make a channel such that if we give different velocities, we can separate the targeted cells at different position of the microchannel. We can have multiple outlets, and based on different frequency, we can separate particular targeted cells. So this study will basically help, and will pave path to the multiple cell separation in the microchannel with vertical position separation in the vertical position against the gravitational forces. Please, if there is any, please ask me.
So I think this would like to call a second presenter, please.
No, so actually, hold on, Sujit.
Okay.
So, Bhaskar or Dhiman, you have any questions? I don't have any question for him.
I don't have any questions either.
Okay, so we can go to the next one. Dhiman, you
No question, no question.
okay, thank you. Okay, let's go to Hi, Joel. Are you sharing your presentation?
Yes, sir, I can.
but we are not able to see the screen.
Yes, sir. I'm just doing. Can you see the screen?
Just hold on, hold on. I think it's coming.
See it now?
Yeah, you can start now.
Okay. Hello. Good afternoon, everyone. My name. I'm a research scholar at IIST Trivandrum. The title of this poster is Novel Polymer MEMS Capacitive Hydrogen Sensor with a Palladium Ring on a Mass Membrane Architecture. So here we have designed and simulated a polymer MEMS capacitive sensor for a gas sensing application. We have used SU8 as a structural layer for the sensor. Here we can see the schematic of the sensor. The sensor consists of a octagon membrane, and it has a rigid mass on top of the membrane and a ring-shaped palladium that is acting as a sensing layer. And the electrode, the top and the bottom electrode, that is situated below the rigid mass, and the gap between the top and the bottom electrode is 2 micron. Now here is the working principle. When the hydrogen is adsorbed by the palladium ring, it will deform the membrane downwards. Now the advantage of our sensor compared to the conventional membrane sensor is that in our sensor, the electrodes will move in parallel with respect to each other. As you can see here in this conventional sensor, the electrode deforms. So the capacitance change is not uniform throughout the electrode area. But in our sensor, the electrodes will not deform but will move in parallel with each other. So the capacitance change will be uniform throughout the electrode area. Now, as you can here we we have simulated the effect of one of our requirement for a sensor design was that the electrodes should move closer to each other during the sensing. To achieve that, we introduced the ring-shaped palladium in this fashion over a membrane. So when a compressive stress is applied, we can see that the membrane will always deform downwards. Another requirement was the parallel movement of the electrodes. To achieve that, we introduced the rigid. So you can see in this graph, when there is no rigid mass, the membrane is completely deforming. There's a curvature. But when the rigid mass thickness is increased from 20 to 25, we see that the profile starts turning parallel. When the rigid mass thickness is above 20 micron, we see a pure parallel profile. So in this region, we have placed our electrode. Based on these parametric studies, we finalized the sensor design. The rigid mass thickness was kept as 20 micron, and the membrane thickness was 7 micron. To simulate the effect of hydrogen absorption on the sensor performance, we use these values of stress on palladium. Now, these values of stress was taken from a literature, from a similar work that was reported earlier. And this is the mechanical and electromechanical analysis. As you can see from the height profile of the membrane, for hydrogen concentration from 0.5 to 4, we can clearly see that the height profile is parallel, that the electrode is not deforming in any form. And this can again be confirmed from the stress profile as seen here. The region below the rigid mass, we can see that a zero stress is induced. So we can confirm that there is no deformation or bending of the electrode. This is the even for 0.5% capacitance change of 198 femtofarad was observed. It is nearly easily detected by commercially available capacitance to voltage converters. So our sensor can even detect easily the hydrogen concentrations which are less than 0.5%. We also did another parametric study to observe the sensor performance when the thickness of the membrane is reduced. So as you can see, it can be seen from the table that when the thickness is reduced, the capacitance change for the stress values also increases. Now here corresponds stress on the palladium film for hydrogen concentrations which are in few hundreds of ppms. So as we see, when the membrane thickness is reduced, the sensitivity probably that the upper limit of detection will be how that was flex. Detection rate and when having
So actually, I have a couple of questions.
Yes, sir.
So generally, these are heated, right, to either to drive out the hydrogen or even to operate. The operating temperature is not at room temperature. So most of your simulations seem to be at room temperature. I mean,
Yes,
could you just
for
comment on?
actually removing the palladium, maybe the heating might be required, but for operation, we don't need that.
Okay, we can't hear you. Can you just stop sharing your screen with us? Answer your question. I think that might be, yeah.
So,
Just answer the question. Yeah.
Yeah, so for operating for detection, we don't need as such temperature. It can operate at room temperature. Maybe for removing the hydrogen, some heating might be required.
Okay. No, you can operate at room temperature, and the temperature of highest sensitivity are two different things. So anyway, so anybody else has questions?
Okay, so I have a small question. So basically,
Yeah.
The
Yes,
results
sir.
you presented, did you do any actual fabrication of the device?
No, sir. Actually, I'm starting the fabrication right now. So I have complete. So I will I will start the
Also
fabrication soon.
Yeah. So
Yeah.
also you mentioned about the gaps basically when there is a absorption happens of hydrogen. So there is a non-uniform gap is there, right, for the capacitive change, and you said that you did something to make it parallel
Yes,
plate kind
sir.
of
Yes, sir.
movement.
So we added a rigid mass on top of the membrane. Yes, sir.
Okay. So is this a new method, or is it reported actually in the literature?
So like this structure for gas sensing is new. For like CMETs and all similar
You know,
structures have been reported.
I feel like making this rigid structure right will make your sensitivity very low. Do you agree with this?
Yes, sir. But since we are using polymer, the sensitivity is higher. So that's what, based on our FEM simulation, we have seen. Like SU8, even with a rigid mass, the sensitivity is very high. I mean, for if we reduce the thickness, the displacements are actually exceeding the air gap.
Okay. Thank you. I think Dhiman, you want to ask something?
No, let's move to the next presentation.
Okay, so we quickly go to the 129. Oh, I think 129 is we have just finished 130. Can you share your presentation, please? Yeah, go ahead, please. Yeah, please go ahead. I think we cannot hear you because your sound is breaking actually. Okay, so actually, except the presenter, all of you, can you please switch off your mic? Mohammed Sahid, can you switch off your mic? And also Vaibhav, you can switch off your mic. Sushil, can you, Mohammed Shahid, can you switch off your
Sir,
mic?
yeah, I told him personally by message, but I think.
Can you remove him from here?
Okay, sir, I'm trying.
Okay, so
Jesma, please make sure कि you have very good audio connectivity. Okay.
Okay, go ahead, please. Oh, still we cannot hear. So okay, what we do? You please log off actually and log in again. We'll go after the next presentation. Okay. Jesma, can you log off now and maybe log in again? I think there is some problem with your mic. Okay, so I think we can go to the next one actually. So which is, I think Sushil, you are the next one, right? Sushil, are you there?
Yes, sir.
Okay, so you have the last presentation, right? 131.
No, not sir. Actually, Subham is approaching me to present. Poster number, sir.
The poster number would be
113.
Yeah, so let him present actually now.
Okay.
Okay, thank you, sir. Is my voice clear?
Yes, now it is good.
Okay, I'm sharing my screen. 1 second. I'm sharing from my mobile because laptop audio quality was not good.
Go ahead, Subham. Go ahead.
Okay. Can you guys see my screen?
Not at Subham. Mohammed Sahid, please switch off your mic, please.
My screen now.
No, we cannot.
Not at
So Shubham, what we'll do is we'll look at your poster and then let's just ask you questions. I think that may be better. You will have your poster and probably you can go through it on the audio and we can
Okay, so
ask you
the
some
title of poster title is electrothermally controlled quantum tunneling based micro cantilever sensor. I will straight away go to sensing scheme. The basic idea is that we use a bimetal cantilever with a tip and along with the contact pad. So we have voltage control also. So basically in the sensing scheme, a laser with a specific frequency chosen for the analyte strikes the solution and gets the laser gets absorbed by the that particular analyte, and then that analyte releases that absorbed energy as heat into the solution, and then this heat causes the bimetal cantilever to bend. And when this bend happens, these deflections happen in the bimetal micro cantilever. The gap between the electrodes changes because these are metal cantilevers. And when the gap between the two electrodes change, this can be sensed as a change in tunneling current. So this is the basic idea, and the simulation was done in COMSOL. And I have a suggested fabrication process also, which is basically using e-beam lithography based liftoff technique. And I have two stages of EBL liftoff. And first stage is for the contact pads, for bottom contact pads. and second stage is for the micro cantilever to be evaporated onto the device. I'll go to the results. The figure 4 actually shows that basically such kind of device is possible from simulation perspective. Basically, this is a deflection of the cantilever on the y-axis and length of the point along length of cantilever on the x-axis. And for different voltages and different temperature, we can different we can just shift in the cantilever deflection. So this basically is showing dual control is possible. Dual control meaning electrostatic control, which is voltage control, and temperature control, which is thermal control. Figure 5 is related to so figure 5, 6, and 7 are related to geometry optimization for cantilever, micro cantilever. So basically, I'm trying to use a bimetal cantilever to plot the sensitivity on the y-axis, which is angstrom per millikelvin per unit for different length, different thickness, and different width of micro cantilever. And these results are quite in line with typical micro cantilever equations. And in the final figure number 8, I am trying to show a tunneling current graph for different materials, where that I have used two extreme combinations which are available. One is the aluminum silver and another is aluminum chromium. So these both show exponential drop in current, but the rate of these exponential drop is different for these two metal combinations. So we can have different sensitivity from millikelvin to even sub-millikelvin temperature range sensitivity is possible, and we can sense those those are deflection. And based on this temperature shift, the tunneling current changes exponentially. So these are the results that I have shown in my poster. Any questions, please?
So Subham, actually one thing is there that your sensing phenomena is based on the gap between the top and bottom electrode in the cantilever, right?
Yes,
So
sir.
which is extremely sensitive to the gap, because the tunneling current or whatever is a very very sensitive to the gap. So and you are using the metal cantilevers also. So how will you control the gaps? Because there are a lot of stress and a lot of issues are there. So to maintain even to get a initial condition where you define your precise gap, don't you feel this is very difficult? How you will manage to get it?
Sir, yes, that is correct. It is difficult, challenging, especially from a fabrication perspective. So basically, the idea is that suppose for typical, so I am also making some cantilevers. So suppose we get a 1 micron or like 500 nanometer curl in the cantilever, then idea is that by varying the voltage and temperature, we can bring it into the tunneling regime. Once it comes in the tunneling regime, which is up to like up to 2 or 3 nanometer between the two electrodes, then we can sense the tunneling current. So that is why where the dual control of electrostatic and thermal control will come into picture to bring that
So,
gap in.
yeah, Subham, maintaining a 2 and 3 nanometer gap actually with the stress, right? So it is next to impossible, I tell you. So, and out of you're talking about the out of plane reflection also. So maybe my suggestion to you is like, maybe if you can think in plane, in plane fabrication, in plane movement, that will help you a little bit, because out of plane and then stress will really play a big role actually in this structure.
Okay, sir. I will look into this in plane details.
Because out of plane, I don't know, maybe others can also comment, but getting 2 or 3 nanometer gap precisely, that is a challenge actually. Have you tried the fabrication at least for the device?
Yes, sir. I have tried some fabrication. Previously, I took this work over from Dr. Nina and that device around 20 nanometers. but that was on beam. I am working with cantilevers, and so far I've with around 1 micron gap, and I am working on to reduce the gap to that level.
So Pushpraj, I think what he will do is maintain a constant turning current by maintaining force feedback. And I think he can do it as long as it's not in the pull-in regime. If it's in the pull-in regime, this control is next to impossible. But if it's not in the pull-in regime, then probably he can maintain constant tunneling current through force feedback. I think that's what. And if the cantilever is curled up, if it's curled down again, it's very hard to do. If it's curled up by default, then it becomes possible.
Okay, okay. I don't have any questions. So you have
Shubham, can you turn off? So there is some background noise coming from somewhere. Not sure who. Shubham, can you turn off? There's a lot of noise coming from your
Okay, sir.
system.
Thank you.
Yeah, I think so. Yeah. Jesma, if you can try again now.
Okay, sir.
Yeah. So I'm not sure if you can see your content this way. Otherwise, we can just look at your poster, I think, again. Like, yeah, we can see much better. Okay. So you have 2 minutes here, in a rush. So please be quick.
Okay, sir. Here we have piezoresistive accelerometer that is having 2 proof masses and 4 intermediate beams in the middle, and 4 external fixed guided beams that are used to anchor the proof mass to a fixed frame. These beams are anchored to the proof mass by means of an extension of the proof mass, which we call as a extended proof mass structure. This structure has the same thickness as that of the proof mass. One significance of including this structure is it improves the mass of the accelerometer by certain amount, and also it reduces the overall length of the beam. The result structure will have a higher resonant frequency as well as a slight improvement in sensitivity. For acceleration in each of the 3 directions, we have 4 piezoresistors. For sensing X and Y acceleration, we have placed the piezoresistors in external beams, and for sensing the Z acceleration, we have placed them in the center of the intermediate beams. Model analysis cells, we have obtained the first 3 working modes of the accelerometer to be due to Z-axis acceleration, Y-axis acceleration, and X-axis acceleration. The first resonant mode was at 18.2 kilohertz. Then in figure, we have illustrated the stress distribution each of them under acceleration X, Y, and Z directions. As we can see in figure 3C, the stress due to Z-axis acceleration causes same amount of tensile stress in all of the intermediate beams. So we are placing 2 piezoresistors for sensing Z-axis acceleration perpendicular orientations to the other 2 piezoresistors. Here we have illustrated the stress profile in one of the external fixed guided beams, that is beam 1. And here we can see that due to X acceleration, we get maximum stress at the end of the beam that is farther away from the proof mass. Whereas due to Y-axis acceleration, we get a almost uniform stress throughout the beam. In order to have a low cross-axis output at the Y Wheatstone bridge, we have placed a piezoresistor at the end of the beam that is nearer to the proof mass. Figure 5 shows the measurement circuit that we use in order to get the output voltage, and we have used 3 full Wheatstone bridges in order to get the output. And in table 1, we have represented the variation in the resistance under the effect of acceleration. In figure 6, we have plotted the output voltage under X, Y, and Z acceleration, and here we can see that the output voltage, that is cross-axis output voltage obtained, is at least 100 times lesser than the prime axis output voltage, and so we have a low cross-axis output. Further, the sensitivity of the device obtained were found to be 37.6 microvolt in X direction, 36.48 74 microvolt per G in Z direction. Then we have done further parametric analysis in order to optimize the device further. The previously proposed device had an intermediate beam length of 100 micrometer, which is illustrated in figure 7a. In order to obtain a higher resonant frequency, it was found that by reducing the length of the intermediate beam to micrometer, we could achieve this resonant frequency. And we have proposed two ways in order to achieve this length of the intermediate beam. In the first model 1, we have reduced the length of the intermediate beam to 50 micrometer without changing the dimensions of other structures in the accelerometer. In the second model, model 2, we have extended the proof mass structure that is present on either side of the intermediate beam further into the intermediate beam. As a result, the overall intermediate beam length is reduced to 50 micrometer. The length of the extended proof mass structure on either side of the intermediate beam is increased. And in table 2 and 3, we have illustrated the results of the resonance frequency as well as the sensitivity. Model 1 has slightly higher resonant frequency compared with that of model 2. However, model 2 is having better sensitivity when we compare with that of the original model. Thus, we have proposed a three-axis accelerometer that is having an twin mass structure. And this, the final model has a resonant frequency of 20 kilohertz, and it has a sensitivity of 38.5 microvolt in the x direction, 37.5 microvolt in the y direction, and 79.7 microvolt in the z direction. Also, by parametric analysis, we have found that by reducing the length of the intermediate beam, extending the proof mass into the beam provides a device that has a better sensitivity compared with that of directly reducing the length of the intermediate beam.
Are there any questions?
No, I don't have any question.
Okay. So me neither. I think that's fine.
We go to the next.
Neem.
Oh.
Neem is here.
No question from us.
Yeah, thank you. That's fine. Okay. Next is, I think last is Sushil.
Sir, may I start?
Yeah, please quickly try and wind up.
Okay, sir.
Sushil, you finish in 2 minutes maximum.
Okay, sir. So, sir, is it my slides are visible?
Yes, go ahead.
We can see your image. We can't see. Yeah, okay.
Okay, so this is the this work is particularly for the MEMS industry. The whole session we were discussing about the how to tackle the stress in the MEMS structure. So this is the reason, and this is the solution we are here to propose. So in this work, particularly we have taken the stress engineering for the MEMS devices as a challenge. So we know in the rightmost section of my presentation, so residual stress is one of the very unwanted kind of parameters or factor in our process, which modify not only the mechanical stuff, but only also modify the pull-in voltage, which is quite important for the low IC applications. So people has already reported the how to deal with this residual stress. So one very popular process is to optimizing the process or developing the bilayer or buffer layer over onto another. And the very prominent solution is the thermal annealing, either through the conventional method or by the rapid thermal annealing. But these methods have the thermal budget issue. We can't go beyond the certain limits, particularly for the CMOS integrated MEMS devices. So here, to simplify this overcomes in the conventional methods, we have uses the laser annealing to tune the residual stress in the MEMS structure. So for that, we have taken the cantilever structure as a test structure, and we try to optimize the parameter of laser in order to achieve the very flattened kind of conformation. So since this work is particularly in the progress of achieving the uniform air gap throughout the suspended electrode for a reliable electrostatic MEM switch. So for that, we have, as I already told, we taken the molybdenum as a structural material, and the gap we have chosen for the air gap is of about 1 micron, and we developed this stage structure by the simple 1 mass lithography system. So here in the left result, you can see the uppermost same. This is the isometric same image of the release structure. In the uppermost same image, you can see because of the residual stress, all our cantilever arrays are curled up. And once we tune our laser annealing at a particular certain dose here, but I'm trying to save the critical energy, we get the completely flattened structures. And so for that, to characterize this, before that, we have carried out a console simulation to interested to know what exactly the temperature is developing at the bottom as well as the top surface of the moly structures. So we found that the temperature is as usually decreases with depth, and at the bottom of the molybdenum surface, the temperature we have calculated about the order of just below 320 degrees Celsius, which is the still limit of thermal budget. And the rightmost example, this is the experimental result. We extract the bending of the cantilever. We have taken the longest cantilever here for the measurement of the length 80 micron. So here we can see without the laser annealing, the bending order was around more than 12 micrometer. But as we keep increasing our energy, and at the energy of 350 millijoule per centimeter square, we got the very optimal flattened structures. Apart from that, we also characterize the structural parameter of the molybdenum, and we found the laser annealing not only giving the flattened structure, but also enhancing the surface roughness and the conductivity. So, so with that, this is the end from my side. Thank you.
Okay, so did you find that? Can you just do the laser annealing just around the anchor and probably do not need to scan the beam? Did you did you scan the whole thing? Or my gut feel is that if you do it only near the anchor point, it should be good enough to give you the flat structure. But anyway, so hello, Sushil. Your mask is your
Yeah. Sorry, sir. Actually, we quite curious to know about what will happen in place of the complete along the length laser annealing, either at the anchor point, as you told, or just at the tip. So this thing we need to exercise, sir.
The other thing, what is the spot size and time period of your pulse? Those things we have not listed.
Sir, the length, the time period was around the 240 microsecond, and the spot size, the single spot size, cover the entire array of the device.
I thought 240 nanometer. It's not that time.
Sorry, sir. It was the wavelength. Sorry.
What it's a pulse thing or it's a DC? How do you? XMR would be pulsed, I believe, but I'm not sure.
Right. It was the pulse laser.
Don't have the time period, right?
Sir, write down. I don't have the handy numbers in mind.
Paper. This is very important. Anyway, so Demand, do you have questions?
Yeah, so the same laser energy was optimal for every cantilever in the array, or did you just optimize it for one particular?
Sir, actually, we did the sorts for the every length of array, but the result, whatever I have showed here, is just for the highest length, which is of the order of 80 micrometer. But we can tune the any length of the dimension of the any cantilever or of any material here.
Okay.
So particularly our result is limited to molybdenum and 80 micrometer length of cantilever only.
you see that if you apply too much dose, does it curl in the opposite direction?
Yeah,
Or does
yes, sir.
Okay.
We found after the certain energy dose, the cantilever goes down and it permanently stick.
Okay.
So we found the both nature of the stress gradient, positive as well as the negative.
Okay, thank you. Okay, so I think everybody we are done here. So thank you very much, and especially for logging in twice. I hope we had a great conference.
Okay, thank you, everybody. So maybe can I ask all the participants to please leave, other than the professors?
Yeah, I think
Who is the Krishna Bala Subramaniam here?
I
Can you
think
please leave?
I think these people have left their systems on and left or something.
Maybe the host can help us to remove.
Hello. Hi. So, host, can you please remove Krishna Balasubramaniam, if possible?
Host is also sleeping, I think. So anyway.
Okay. So, I think we have. Okay.
Yeah,
So, can you see the highlighted ones in the green?
yeah, but the last one has the maximum marks.
Yeah,
Okay.
yeah. I also
Okay.
feel last one.
Okay. So, actually, truly speaking, we are only having two with the highest numbers. So, basically, the one is this.
Yeah, one with the highest number. I think only one has got 18. Others have got 17, I think.
Okay, so maybe before we make a decision, because oh yeah, now 8 and 9. But can you comment, like Dhiman, about this poster 115?
Venkat,
How
can
this
you log out, please? Vaibhav Rana, can you log out?
Vaibhav, can you log off now?
And
Hello,
I think
Vaibhav.
this discussion is live also, so that's another thing.
Okay, so then do you want to discuss? Okay, so how?
Maybe we can move to Teams.
Okay, yeah, sure, sure. Let's meet in the team then.
Okay, yeah, thank you.
Let's leave now. Okay.